You're sitting cross-legged in the middle of a concept so vast it doesn't even pretend to play fair. Infinity. It isn't a number. You can't grab it, count to it, or pin it down. But somehow, it shows up everywhere. On calculators, in classrooms, and even inside your dreams. You've seen it before. That sideways figure 8 symbol. Smooth, mysterious, slightly smug. But what does it really mean? Hey guys, close your eyes. And let's drift back to complex math. Tonight, we wander through infinity. Softly, slowly. Picture a hotel. Not just any hotel. Hilbert's Hotel. It has infinite rooms. Every single one is full. And yet, somehow, you can still check in. The desk clerk just moves every guest over by one room. And voila, space for you. That's infinity's first magic trick. It always has room, even when it's full. Cheeky. Here's the twist. Not all infinities are created equal. There's the infinity of whole numbers, 1, 2, 3, and so on. But then there's the infinity between 0 and 1. Turns out, there are more numbers squished in that tiny slice than in the whole infinite sea of counting numbers. How? Well, scientists still argue whether more even makes sense here. But Georg Cantor, the godfather of infinity math, proved it anyway, using only logic and an aggressively sleepy pen. And here's your quirky bedtime tidbit. Cantor's obsession with infinity drove him mad, like actual asylum mad. He kept trying to map out how big forever really is. And it turns out, forever has layers like an onion, or a bureaucracy. You can almost feel it now, this strange, echoing concept curling around your thoughts. It's not just a big number, it's something else entirely. A horizon you never reach, a staircase you climb forever, and no matter how far you get, it winks and says, there's always more. Before we dive any deeper, if you're enjoying this so far, feel free to like the video and subscribe. It really helps, but only if it feels right to you. And if you're up for it, drop your location and local time in the comments. I always enjoy seeing where in the world you're listening from. Now then, let's wander into a place where logic eats itself. You step carefully into a quiet library, the shelves packed with books that whisper paradoxes as you pass. One book stands out. It's titled The Catalogue of All Catalogues That Don't List Themselves. You open it slowly, then blink. If it includes itself, it doesn't belong. But if it doesn't include itself, well, then it does. Congratulations. You've just walked into Russell's paradox. This odd little loop cracked the foundations of math wide open. A guy named Bertrand Russell was trying to tidy up logic, get everything neat and self-contained. But when he tried to define a set of all sets that don't contain themselves, he accidentally short-circuited the whole system. It's like inventing a broom that refuses to sweep itself. And this wasn't just an abstract hiccup, it was an earthquake. Before Russell, math thought it had rules, definitions, clean lines. But this paradox, simple, elegant, and deeply annoying, revealed that logic could twist itself into a pretzel if you weren't careful. Scientists still argue whether our modern logic systems truly escape this trap, or if they just put a fancier label on the can of worms. We built fences, we made categories, but the ghost of Russell's paradox still lingers, peeking around corners and softly snickering. Here's your quirky tidbit. This whole mess partly inspired the creation of computer languages. If you've ever seen an error message on your screen that says, recursive reference detected, you owe that little moment of frustration to Mr. Russell's brain loop. So tonight, as you drift deeper, Imagine thought itself folding in on itself, like a cat trying to catch its own tail. Infinite reflection, no resolution, just a puzzle that smiles back at you forever. You slide gently into a dimension where numbers pretend to be real, but aren't. Tonight's guide? The square root of -1. Yes, really. You've heard of it before. I, the imaginary unit. But don't let the name fool you. These numbers may sound like they belong in a fantasy novel, but they power the entire digital world. Your phone, your internet, your microwave. They all whisper to imaginary numbers behind your back. Here's the problem. There's no real number you can square to get a negative result. Not one. Try it. Positive times positive, positive. Negative times negative, still positive. It's like math refuses to frown. But mathematicians, stubborn little dreamers that they are, decided to invent a new kind of number. One that could break this rule. That number is I, defined as the square root of 1. From there, a whole universe unfolded. Suddenly, we had complex numbers, numbers made of two parts, one real and one imaginary, like 3 plus 2i. It sounds like gibberish, until you realize it unlocks answers that real numbers never could. You've probably used electricity today, right? Or watched a YouTube video, maybe this one. Well, imaginary numbers help describe how waves move. Light, sound, voltage. They're like secret agents for rotation and flow. Even quantum physics needs them. It's ironic. We call them imaginary, but the world wouldn't work without them. And here's your quirky tidbit. In 1843, the mathematician William Rowan Hamilton carved the formula for quaternions, a cousin of complex numbers, into a bridge in Dublin because he was so excited about discovering them. Yes, he vandalized public property in the name of math. Scientists still argue whether imaginary numbers are real, not mathematically, but philosophically. Are they just a tool? Or do they describe something deep and unseen? For now, all you need to know is this. In math, even the imaginary can be essential. So breathe in, breathe out, and let your mind balance gently between the real and the unreal. Let your mind wander now into a shape that never ends. You're walking along a coastline, but the more you zoom in, the more there is. Every rock splits into pebbles, every pebble into grains, every grain into jagged edges that defy smoothness. You're inside a fractal now, a pattern that repeats itself no matter how close you look. Nature's never-ending doodle. Fractals are the rebels of geometry. While classic shapes love clean lines and smooth curves, fractals thrive on chaos, jagged, recursive, infinite. Think of a snowflake, or a head of Romanesco broccoli, or the swirling pattern in your fingerprint. These aren't just random, they follow rules, deep looping rules. One of the most famous is the Mandelbrot set, a swirl of psychedelic shapes that, when you zoom in, just keeps going. It's like math is painting with an infinite brush, and it never runs out of ink. Even the tiniest pixel hides galaxies of detail. But fractals aren't just pretty. They help describe real-world messiness, mountain ranges, lightning bolts, blood vessels. Traditional math couldn't capture the raw texture of reality. Fractals said, "Hold my asymptote," and did it anyway. Quirky tidbit. In the 1980s, fractals were used to generate landscapes in early video games and CGI. That rolling terrain you flew over in old-school simulators. Probably pure Mandelbrot. Scientists still argue whether fractals are embedded in reality itself, or if they're just how our brains choose to interpret natural complexity. Are clouds actually fractal, or do we just like seeing patterns in fluff? Either way, as you relax deeper, imagine your thoughts curling into recursive loops, a spiral inside a spiral, like tree branches splitting under moonlight, a dream that reflects itself forever. You've now left the land of perfect circles and polite squares. Fractals are here. They're weird. They're beautiful. And you've never quite left them behind. Tonight, you're not made of stardust. You're made of functions. Imagine your body as a quiet little math machine. You put in a number, say how much coffee you drank, and out comes a result, your heart rate. That's a function, a process. An elegant little rule that says, if you give me this, I'll give you that. Functions are everywhere. You feed them input. They return output. The world runs on them quietly. Your GPS, a function. Your TikTok algorithm, a terrifying, mysterious, slightly judgmental function. Even your sleep pattern, or lack thereof, has one lurking behind it. Let's keep it cozy though. Picture a function as a vending machine. You press B7, and out comes a soda. Press B7 again, and it's the same soda. Predictable, consistent. That's what makes a function a function. Every input has exactly one output. Math loves commitment, but then things get funky. Some functions are smooth and curvy, like a gentle hill. Others are jagged, chaotic, and wildly unfair. You might give two similar inputs and get totally different results. Some functions won't even let you in, like a grumpy bouncer that says, "Sorry, we don't take square roots of negative numbers here." There's one type of function, called an identity function, that just gives you back exactly what you gave it. Input 5, output 5. It's the math equivalent of a mirror. Others might flip your input upside down, stretch it, reverse it, or send it spiraling into an imaginary dimension. Math is a drama queen like that. Here's a quirky tidbit. There are functions so bizarre, they're continuous everywhere, but differentiable nowhere. They look smooth from a distance, but up close, pure static, like a velvet painting made of chaos. Scientists still argue whether functions should always behave nicely, or if the truly wild ones deserve more respect. And really, who gets to define behaving anyway? So as you drift now, imagine your thoughts like gentle inputs into a sleepy function, processed softly, sent out into the void as warm, humming answers. Sink deeper now, into the quiet edge where things almost happen, but never quite do. You're standing on a bridge between two worlds. Behind you, numbers you understand. Ahead, a cliff, where values approach a point, but never touch it. Welcome to the land of limits. This is where math holds its breath and whispers, almost. A limit asks, what happens as you get really, really close to something? You never actually arrive. You just sneak up beside it, like a cat stalking a beam of sunlight. It's how we deal with impossibilities, dividing by zero, defining motion, even calculus itself. Limits are the poetic loophole math uses to explain change. Imagine pouring tea into a cup forever, but each time, you pour only half of what's left. Half, then half again, then again. You'll never overflow the cup. That's a limit. Infinite steps, but a finite result. A dance of approaching without touching. But sometimes, limits get nasty. They can explode to infinity, or vanish into undefined chaos. Mathematicians invented whole tools, like L'Hopital's rule, just to deal with these sleepy little rebels. It's like math knew it needed therapy. And here's a fun, quirky twist. The limit concept is so central to calculus that Newton and Leibniz, two brilliant, possibly petty men, both fought over who invented it. The debate still smolders today, like two ghosts side-eyeing each other in the afterlife. Scientists still argue whether limits are real phenomena or just a trick of language. Are we describing nature, or just our best guess about it? You can get infinitely close to understanding, but the final answer keeps slipping out of reach. So tonight, imagine walking a narrow path, each step smaller than the last. You move forever, and yet you never arrive. That's the limit. Gentle, mysterious, almost touching something beautiful, but choosing instead to glide around it in silence. Take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and local time in the comments. I love seeing where in the world you're falling asleep from. Now you're drifting into the warm, swirling tide of change itself. This is calculus, but not the teeth-grinding textbook version. No quizzes, no crying, just the soft idea that everything changes, and math wants to understand how. At its heart, calculus is made of two sleepy questions. First, how fast is something changing? That's the derivative whispering secrets about slopes, rates, and speed. Second, what's the total effect of all these little changes? That's the integral, scooping up tiny pieces and stacking them into something whole. It's basically a math hug. Imagine watching raindrops roll down a window. Some speed up, others slow down. Calculus watches every drip and murmurs, "I know exactly what you're doing." You can't always see it, but calculus is tracing curves, calculating shadows, measuring chaos with elegance. It started with falling apples. Newton wanted to understand gravity, not just that it happens, but how fast it pulls you. He needed a tool to describe motion. Enter calculus. Then Leibniz, working independently, and maybe with more dramatic flair, built his own version. That sparked one of history's pettiest mathematical rivalries. Even today, some textbooks lean Newtonian. Others stick with Leibniz's squiggly style. Academic shade lasts centuries. Here's a quirky tidbit. Integrals were used in the 1700s to calculate the exact shape of a hanging chain, not just for art, but for designing bridges. Turns out, sleepy math curves can hold up real-world steel. Scientists still argue whether calculus was discovered or invented. Did it always exist, quietly shaping nature, waiting to be found? Or did humans build it, pixel by pixel, like digital scaffolding around reality? Either way, tonight it doesn't matter. Just imagine your thoughts like soft curves, sometimes rising, sometimes falling. Everything you feel, every breath you take, is a gentle slope. You're not standing still. You're moving, always changing. And calculus is there, tracing your outline as you dream. Let's check into the weirdest hotel you'll never leave. You shuffle up to the front desk of Hilbert's Hotel, your suitcase squeaking quietly behind you. The clerk, a moustached fellow with infinite patience, says all the rooms are full. But don't worry, there's always space for one more, because this isn't an ordinary hotel. It has infinite rooms, literally. This famous thought experiment, dreamt up by David Hilbert, is a gentle prank on common sense. Say every room is taken, room 1, room 2, room 3, and yet, somehow, you can still be checked in. The clerk just moves each guest from room N to room N+1. Boom. Room 1 is free. You could even show up with a tour bus of infinite new guests. No problem. He'll shift everyone again. That's infinity's weird trick, being full and still having room, cozy and confusing. And it doesn't stop there. What if an infinite number of infinite buses showed up, each with infinite guests? Well, the math gets weird. But yep, there's still room. Infinity isn't just big. It's flexible. A little too flexible, maybe. Here's your quirky tidbit. Some mathematicians genuinely use ideas like Hilbert's hotel to think about the universe. Whether it's infinite, how particles behave, or even how time might loop. This dusty old hotel has more science cred than most real ones. Scientists still argue whether this kind of actual infinity really exists in the universe, or if it's just a mind game. Can something be infinite in reality? Or is that just math being dramatic again? For now, you're just a sleepy traveler. You've been checked into a room that doesn't really exist, in a hotel that never ends, with neighbors who stretch off into forever. Pull up the covers, fluff the infinite pillows, and let the bizarre logic of this place rock you to sleep. Tonight, gravity doesn't pull you down. It pulls you into calculus. Picture yourself beneath an apple tree, not some enchanted one, just a regular sun-dappled orchard with the grass cool beneath you. An apple falls, plop, simple. But what if you wanted to describe that fall, not just watch it? Exactly how fast it drops, how far it travels in each heartbeat. That's where Newton steps in, grinning, probably tired, definitely a bit obsessed. He wasn't the first to notice gravity, but he was the first to wrap it in math, turning falling apples into a system of laws, precise and elegant. With calculus, he didn't just say, things fall. He said, here's the function of their fall. Derivatives and integrals became his sketchpad for the universe. The story is probably apocryphal. No one's sure if an apple really hit his head. But it's such a good story, we let it live rent-free in our cultural memory. Scientists still argue whether Newton invented calculus independently of Leibniz, or if both men borrowed a bit more than they admitted. Either way, they both took the same raw idea, change, and turned it into a tool so powerful it could model planetary orbits and swinging pendulums. Here's a quirky tidbit. Newton was a master of silence. He didn't publish his major math work for years. In fact, when he did share it, it caused such drama in the math world that people stopped inviting each other to dinner over it. But his calculus didn't stay in space. It trickled down into economics, biology, engineering, even the rhythm of your heartbeat. Everything that moves, grows, or flows, Newton gave math the language to describe it. So as you lie there, imagine yourself not as a static being, but as a function in motion. Every breath, a curve. Every thought, a rate of change. You're not just feeling gravity, you're understanding it. Softly, sleepily, like Newton might have, under a shady tree. Let's bend the number line until it argues with itself. You're floating gently above what you thought was a straight, dependable highway of numbers. Your old friend, the number line. Left for negatives, right for positives, zero in the middle like a tired referee. But suddenly, that line curves, warps, folds in on itself like soft taffy. Welcome to non-Euclidean geometry, where straight lines are just suggestions. In Euclidean geometry, the one you learned in school, parallel lines never meet, and the angles of a triangle always add up to 180 degrees. Feels comforting, right? But when you leave flat land and drift into curved space, those rules fall apart like a soggy pop quiz. On a sphere like Earth, triangles get greedy. Their angles can add up to more than 180. And parallel lines? Try drawing two straight paths from the equator to the North Pole. They'll meet, no matter how hard they try to stay apart. Geometry gets moody, and it doesn't stop at spheres. There's also hyperbolic space, a wild, saddle-shaped universe where everything stretches like it's being gently pulled apart. In hyperbolic space, even the idea of straight feels like a prank. Artists like M.C. Escher loved it. Those endless tiling patterns that look like dreams drawn by math itself. Here's your quirky tidbit. Lobachevsky, one of the pioneers of non-Euclidean geometry, was so mocked for his ideas that people turned his name into a joke. Until a century later, when Einstein showed that space itself is curved. Suddenly, Lobachevsky didn't look so ridiculous. Scientists still argue whether space is truly non-Euclidean, or if it only appears curved due to gravity. Einstein's theory of general relativity gave curved space a shiny new purpose. It explained gravity not as a force, but as the shape of space-time itself. So as you drift now, let go of flat surfaces and perfect shapes. Let the number line curve gently beneath you, carrying your thoughts into the flexible, dreamy fabric of space. Now imagine running forever and never catching a turtle. You're standing on a track, stretching into the haze. Ahead, a turtle plods slowly. You're faster, way faster. But every time you reach where the turtle was, it's already moved a bit farther ahead. This is Zeno's paradox, the ancient thought experiment that says motion is impossible. Which is weird, because, well, you're moving. Zeno of Elea, a Greek philosopher with too much free time and a love for cosmic trolling, posed this brain pretzel to argue that change, motion, and time itself might be illusions. He imagined dividing distance into infinite steps. And since infinity has no end, you'd never finish crossing even a small gap. Makes sense in theory. Less so when you're trying to chase a pizza delivery. This paradox isn't about speed. It's about how math handles infinity. To solve it, you need something we just learned about: limits. By adding up those infinite little steps using a limit, calculus saves the day. Infinite parts can still lead to a finite whole. Achilles does catch the turtle. Probably wins a gold medal too. Here's your quirky tidbit. Zeno's paradoxes confuse people for over 2,000 years. And honestly, they're still kind of annoying. One variation says you can never actually start walking across a room because you'd first have to go halfway, then half of that forever. Math's version of "are we there yet?" is you can't even leave. Scientists still argue whether time flows continuously or in tiny, indivisible chunks, called chronons by some quantum theorists. If time is grainy, Zeno might have been right, sort of. So picture yourself on that infinite track. With each breath, you cover half the distance, then half again. Yet somehow, you arrive. You beat the paradox. Or maybe it just gave up. Either way, your sleepy journey moves forward, even if Zeno still doesn't believe it. Let's roll softly into the most delicious constant in the universe. You're drifting now through the curves of a perfect circle. Round, balanced, infinite, and right at the heart of it all. Pan, that quirky, irrational, unstoppable number that starts with 3.14 and just keeps going, forever, without repeating. You've seen it before, scribbled in textbooks, flaunted on t-shirts, maybe even celebrated on March 14th. But tonight, let's understand why circles are addicted to it. P is the ratio of a circle's circumference to its diameter. Simple, right? But that's just the polite surface. Underneath, P shows up everywhere. Waves, probabilities, music, quantum physics. It's like P crashed the math party, stole the mic, and never left. Imagine drawing a circle. As your pencil glides around, it's secretly tracing out P again and again. It's the fingerprint of roundness, the DNA of curves. And since circles show up in so many places, planets, atoms, puddles, pizza, ends up hidden in nearly every field of science. Here's a quirky bedtime tidbit. P has been calculated to over 100 trillion digits, and yet we still don't know everything about it. People run massive computer projects just to find the next digit. Why? No one's sure. It's part math, part obsession, part therapy. And yet, P doesn't play fair. It's irrational. It can't be written as a simple fraction. It's also transcendental, meaning it's not the solution to any algebraic equation made of whole numbers. In math terms, it's the cool, emotionally distant loner who can't be boxed in. Scientists still argue whether there's a pattern deep inside P's digits. So far, nothing. It's pure chaos. But maybe, just maybe, there's a cosmic code waiting to be cracked. So as you drift now, picture yourself spinning slowly around a circle. Each lap brings you a little closer to understanding, even if P never ends. It's not about reaching the final digit. It's about the soft, infinite rhythm of going around, and around, and around. Now let's melt some geometry until breakfast gets involved. You're holding a donut. Not just any donut. A mathematical one. Soft, sweet, with a hole in the middle and mysterious secrets hidden in its curves. Across from it sits a coffee cup. Ordinary. Handle on one side. But in the eyes of topology, these two are identical. This is not a sugar-fueled fever dream. This is topology, the study of shapes that can stretch, bend, twist, and morph, as long as they don't tear or glue themselves shut. And in this stretchy world, a donut and a coffee mug are the same shape. One whole, one continuous surface. If you were made of rubber, you could smush and reshape one into the other without breaking a single atom. Topology is geometry's dreamy, rule-breaking cousin. It doesn't care about straight lines or sharp angles. It only cares about connections, holes, surfaces, twists. Two objects are considered equivalent if you can transform one into the other by gently stretching it like pizza dough. Here's your quirky tidbit. Mathematicians lovingly call this the donut coffee cup problem. There are even plush toys and memes about it. It's probably the only time math has been used to justify carbs. But topology gets wild fast. There are shapes with multiple holes, shapes that loop into themselves like Mobius strips, and shapes that exist in 4 or more dimensions. Some are so weird they only live in math's imagination. Creatures like the Klein bottle, which turns itself inside out without having an inside or outside. Scientists still argue how far topology can stretch, literally and metaphorically. Can the universe itself be understood topologically? Is space a torus, a hypersphere, something weirder? So as you drift now, picture yourself reshaping quietly. Your thoughts, once sharp, now curve and soften. Your logic bends into loops. You, like the donut, are gently becoming something new, warm, strange, and totally connected. Let's sit by the fireplace and ask a question that annoyed your middle school brain. Why does a negative times a negative equal a positive? You've heard the rule. You might have memorized it. But chances are, no one ever told you why. It just showed up on a quiz one day, like an uninvited guest at your mental dinner party. But tonight, we're going to unravel it. gently, like peeling a sticker off a dusty notebook. First, think of multiplication as repeated addition. 2 times 3 means 2 groups of 3. But once we hit negatives, things go sideways. What's negative 2 times negative 3? You're not just subtracting anymore. You're flipping direction. Imagine you're standing still, facing backward. Then someone says, now walk backward, while still facing backward. You're going forward. That's what multiplying 2 negatives does. It flips the flip. Backward of backward becomes forward. Like using 2 mirrors to see the truth. Here's your quirky bedtime tidbit. Some early mathematicians resisted negative numbers entirely. They thought negatives were absurd and refused to accept them as real. It wasn't until the 1800s that negatives got full legal citizenship in the land of numbers. But wait, it's not just a rule of convenience. This double negative into a positive rule has to work if we want math to stay consistent. If it didn't, the whole system would collapse like a poorly built pillow fort. It's part of the deeper structure that makes algebra, well, not totally chaotic. Scientists still argue how best to teach this without making kids hate life. Is it better to explain it geometrically? With money? With debts and time travel? No one agrees, but everyone agrees it matters. So now, as your thoughts slow down, picture negative numbers like little arrows pointing one way or another. And when 2 of those arrows flip each other, you end up moving forward. Peaceful, predictable. Math's way of keeping balance in its strange, dreamy world. Tonight, we peer into the personalities of numbers. You're lying on your back, counting stars, or at least trying to. But some stars are loners. They don't divide evenly, they don't follow the crowd, and they don't share. These are the primes, the rebels of the number world. Prime numbers are those whole numbers greater than 1 that can only be divided evenly by themselves and the 1. 2 is the smallest. 3 nods quietly behind it. 5 gives you a slow, knowing wink. They're scattered across the number line like cosmic static. No pattern, no rhythm, just there. Now picture the even numbers. Calm, reliable. They double up perfectly. The odds? A bit more wild, a little lopsided. But primes? They're unpredictable. You can go for stretches with no primes at all, and then bam, a whole cluster. It's like they enjoy hiding just to see if anyone's paying attention. Here's your quirky tidbit. The ancient Greeks discovered a proof that there are infinitely many primes, but we still don't know the exact pattern they follow. It's like knowing there are always more fireflies in the field, but never being able to predict where the next one will blink. Scientists still argue over the Riemann hypothesis, one of math's most famous unsolved problems. It's all about understanding the secret distribution of prime numbers. Solve it, and you get $1 million. Or a lifetime of polite confusion, depending on how society values deep theoretical math. But primes aren't just fun to think about. They're also vital. Your data, passwords, and online banking are protected by them. Modern cryptography is built on the idea that it's really hard to factor large numbers into their prime components. Primes, it turns out, are also elite bodyguards. So as you drift now, think of the numbers tucked around you, not just as digits, but as personalities. Some quiet, some predictable, some mischievous and proud of it. And out there, scattered like dreams across the infinite, the primes shine, alone, but never lonely. Let's return to the quiet world of triangles, where secrets hide in straight lines. You find yourself drawing on soft paper, sketching a right triangle, one side here, another there, and the longest side, the one across from the 90-degree corner, stretches out like it knows something you don't. That's the hypotenuse, geometry's dramatic flair. And tonight, it whispers Pythagoras. The Pythagorean theorem says that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. You've heard it. A squared plus B squared equals C squared. But don't worry, we're not doing math tonight. We're feeling it. Picture a ladder leaning against a wall, or a tree casting a shadow across a meadow. In each case, you've got a triangle, one that's humming this old Greek lullaby. It's everywhere. Architecture, construction, even video games. Triangles make things stable, solid, knowable. They're nature's little anchors. But here's the twist. Triangles have drama too. There are right triangles, obtuse triangles, equilateral ones, and each with their own quirks. Right triangles just happen to be the cleanest, most mathematically elegant of the bunch. That's probably why Pythagoras claimed them like a band claiming their hit single. Here's your quirky tidbit. Legend says Pythagoras was so obsessed with math and harmony that he banned beans from his school. Actual beans. No explanation. Possibly a metaphor. Possibly not. Ancient math had serious dietary opinions. Scientists still argue how much of the Pythagorean legacy was real and how much was legend passed down like sleepy campfire stories. But one thing's certain, the theorem works. Always has, always will. In our dimension, at least. So as you sink deeper into your pillow, imagine lying across that hypotenuse, supported by the calm certainty of two sides that trust each other completely. The triangle doesn't waver. It doesn't lie. It just is, simple, balanced, perfect. You're walking through a pine forest now, but something's strange. The cones on the ground, the branches above, even the swirl of petals on nearby flowers, they all follow the same spiral, a gentle, graceful twist that seems too perfect to be random. Welcome to the Fibonacci sequence, nature's favorite playlist on repeat. It starts simply enough. 0, 1, 1, 2, 3, 5, 8, 13. Each number is the sum of the two before it. That's it. But from that humble beginning springs a mathematical pattern that's everywhere. Petals on a daisy, scales on a pineapple, spirals in galaxies. It's like the universe chose one rhythm and just ran with it. Fibonacci didn't invent the sequence, he just introduced it to the Western world while trying to solve a word problem about rabbit reproduction. Because of course. But the pattern existed long before that, lurking in Hindu Arabic mathematics, hidden in ancient architecture, maybe even baked into the DNA of life itself. Here's your quirky tidbit. The Fibonacci sequence connects closely with the golden ratio, that irrational number, about 1.618, famous for being the most beautiful proportion. As the Fibonacci numbers get bigger, the ratio between each pair starts to approach the golden ratio, like a moth circling a porch light. Scientists still argue whether nature uses Fibonacci deliberately, or whether our brains just love seeing spirals and assigning meaning to them. Are sunflowers actually calculating? Or are we just very good at spotting patterns in the noise? Either way, it's comforting. This soft spiral tucked into everything, subtle, patient, mathematical. It doesn't shout. It doesn't demand. It just appears again and again, like a quiet reassurance that there's structure under the chaos. So tonight, as your thoughts begin to curl inward, imagine those spirals, branching, blooming, spreading out from your breath. Fibonacci isn't a formula anymore. It's a lullaby. Let's step into the hazy edge of forever, because tonight we're going to count to infinity. Not just once, multiple times. Because, believe it or not, there's more than one kind of infinity. And some infinities are bigger than others. Which sounds like a math joke, but isn't. You begin with the natural numbers, 1, 2, 3, and so on. A familiar, dependable infinity. You could keep counting forever, and you'd never reach the end. Mathematicians call this set countably infinite. It's like an endless line of marbles, each numbered, each one with a place. Now imagine trying to count all the real numbers between 0 and 1. Sounds smaller, right? Just one little interval. But nope, this infinity is even bigger. Because between every two real numbers, there's another real number. And between those, another one. You can't list them all, even if you had forever and a very patient assistant. This was discovered by Georg Cantor, the same guy who gave us Hilbert's Hotel. He proved, using pure logic, that the real numbers can't be matched one-to-one with the counting numbers. There are just more of them. Like trying to match stars in the sky with grains of sand and realizing the sky's winning. Here's your quirky tidbit. Cantor's work was so radical, many of his contemporaries refused to accept it. Some thought he'd broken math. Others just ignored him entirely. Eventually, he was hospitalized for depression, haunted maybe by the enormity of the infinite. Scientists still argue about the nature of these infinities. Is there a smallest uncountable infinity? How many sizes of infinite actually exist? These questions lead to some of the strangest corners of set theory, places where logic wears pajamas and wanders around half asleep. So tonight, as you rest your head, imagine numbers stretching out in every direction. Some march in order, others swirl and shimmer in unlistable silence. And somewhere, beyond all counting, infinity hums, bigger than big, and still not done. Let's pull back the curtain on the math world's favorite game of hide and seek. You're sitting in a dusty classroom, and someone draws a big X on the board. Solve for X, they say, as if that's supposed to mean something. And suddenly, you realize X is always hiding something. It's the masked stranger of the equation world. This is algebra, the part of math where we take something we don't know and give it a name like X or Y, and then casually pretend we understand it. It started thousands of years ago with ancient Babylonians solving word problems using symbols. Then a Persian mathematician named Al-Khwarizmi came along and gave it structure. His name, by the way, gave us the word algorithm. Yep, he's the reason your phone knows what ads to show you. In algebra, we build little puzzles. You're given part of the picture, and you work backward to fill in the blanks, like reverse engineering a recipe by licking the spoon. And yet, algebra is less about solving than about expressing. Want to describe the slope of a mountain? That's algebra. Want to model population growth, loan payments, or how fast your coffee cools down? Algebra again. It's math's storytelling language. Here's your quirky tidbit. X became the go-to symbol for the unknown, partly because of a translation hiccup. When Arabic texts were translated into Spanish, the word for something was written with a esh sound that didn't exist in Spanish, so they used X instead. A linguistic shrug that stuck for centuries. Scientists still argue whether algebra should be taught with real-life applications from the start, or if we should just dive into the symbolism and let meaning catch up later. Either way, X remains the math world's best-kept secret. So tonight, let X be whatever you want it to be. Let it float just out of reach, mysterious, calm, unknowable. You don't have to solve for it now. Just know it's there, waiting quietly in the shadows of the equation, like a question mark in disguise. Tonight, let's pick sides. Are you even, or are you odd? As you drift, numbers begin to sort themselves quietly. Some like to be shared equally, split down the middle, balanced. These are the even numbers, 2, 4, 6, marching in pairs like polite dinner guests. Then come the odd numbers, 3, 5, 7, walking in lopsided rhythm, a little off, a little playful, refusing to divide cleanly. Parity, the study of evenness and oddness, seems like a simple sorting game, but it hides deeper layers. In coding, parity helps detect errors in data. In chess, parity determines who has the advantage in endgames. And in number theory, it's used to crack ancient problems wide open. Even the universe seems to care. Particle physics has a thing called parity violation, where certain reactions behave differently when mirrored, suggesting that maybe the cosmos has a favorite side. Think of it like this. Evens are symmetrical, calm, predictable, but odds, they're rule breakers. The first prime number is odd. Most Fibonacci numbers are odd. Odds carry a little swagger in their step. Here's your quirky tidbit. In some ancient numerology systems, even numbers were considered feminine, balanced and nurturing, while odd numbers were male, restless and creative. Basically, people were assigning personalities to digits before it was cool. Scientists still argue about whether parity-related properties might help solve some of math's deepest mysteries, like the Collat's conjecture, a deceptively simple game involving odd and even numbers that no one's been able to solve. You take a number. If it's even, divide by 2. If it's odd, triple it and add 1. Repeat. Eventually, you always seem to land at 1. But no one knows why. So tonight, as you slip further into the dark, imagine numbers lining up, evens to one side, odds to the other. A quiet, endless dance of symmetry and surprise. And you, curled in the space between, right where order meets the unexpected. Tonight, we roll gently around the perfect curve of a circle. You're sitting on the edge of a still pond. You drop a pebble, and ripples spread out in perfect circles, soft, even, endless. The circle is the purest shape in math. No corners, no edges, just motion and balance, repeating forever. A circle is defined by its center and its radius. From that quiet middle point, every part of the edge is the same distance away. That's what makes it so special, so fair. If shapes had morals, the circle would be the philosopher. But it doesn't stop at radius. Circles are full of quiet secrets. There are chords, lines that slice across the circle, diameters, the longest of those chords, arcs, the soft portions of its edge, tangents, lines that brush the circle's cheek and then glide away, all of them dancing together in a quiet relationship older than language, and angles. Oh, circles love those. Every angle inside or around a circle tells a story. The central angle, the inscribed angle, the angle that turns a wheel or measures your favorite pizza slice. There's a reason we measure angles in degrees, 360 of them, thanks to ancient Babylonians who liked round numbers and clear skies. Here's your quirky tidbit. Your clock, your compass, your entire concept of navigation, those all rely on circles. Even your sense of time loops in a circle. Noon becomes midnight, becomes noon again. Every tick of the second hand is a tiny act of circular geometry. Scientists still argue about the origins of why the circle feels so naturally perfect. Is it evolutionary, a trick of our senses, or does the universe itself favor roundness, like the planets, atoms, or even the orbits of thoughts? So as you sink into sleep, imagine yourself gliding along a circle's edge. No sharp turns, no endpoints, just smooth, unbroken movement. And somewhere in that orbit, you begin to forget where the beginning was, or if there even was one. Now we meet the quiet genius that hides behind the scenes. E, the most important number you've barely met. You're standing beside a tree, watching it grow. Each year, it gets a little taller, a little wider. But what if, instead of growing in chunks, it grew continuously, little by little, every moment, with no pause? That's what E describes. It's the number behind growth that never sleeps. Like P, E is irrational. It starts with 2.718 and never repeats, never ends. But unlike P, which rules circles, E rules growth, decay, and compounding. It pops up in populations, interest rates, radioactive decay, bacteria, your coffee cooling down, and even how a rumor spreads through a sleepy village. The magic of E becomes clearest in continuous compounding. Imagine $1 earning interest. If it compounds once a year, you get a bit more. If it compounds monthly, a little more than that. But if it compounds infinitely often, it tells you the limit of how much that dollar can grow in a year. It's the perfect growth number. Quiet, precise, extremely smug. Here's your quirky tidbit. E was first stumbled upon by Jacob Bernoulli, who was trying to solve a problem about, you guessed it, compound interest. The number appeared like a ghost in his equations, whispering, "Hey, I'm important now." Scientists still argue about how to explain E in a way that feels intuitive. Some say it's about slopes and tangents. Others say it's the natural result of slicing time into infinite pieces. Either way, the number keeps showing up, like a surprise guest who always brings useful snacks. So tonight, let your thoughts drift like exponential curves, starting slow, then rising gently, endlessly. Picture growth without boundaries, decay without finality, a number that never stops moving, never stops reaching. And there, riding that smooth wave, is E, not flashy, not loud, but undeniably everywhere. Now let's slip softly into the future, where math quietly makes predictions. You're staring at a pond again, but this time you toss in a leaf and watch it drift. You want to know where it'll end up, how fast it'll move, whether it'll spiral into the shore or keep spinning forever. That's where differential equations come in, math's crystal ball. A differential equation doesn't just describe where something is, it describes how it's changing. It's a whisper about what comes next. Think population growth, the way heat spreads across a room, or how a planet orbits a star. These equations tell us how systems evolve step by tiny step. They're built around derivatives, the math of change. If calculus is the study of motion, differential equations are motion in action. They model hurricanes, heartbeats, pandemics, and coffee temperatures, again. If it changes over time, chances are it's hiding a differential equation under the surface. Here's your quirky tidbit. The same type of differential equation can describe wildly different things. The spread of a disease and the cooling of a cup of tea can be modeled using eerily similar math. It's like the universe reuses its code. But solving them? That's the tricky part. Some are neat and tidy, like a lullaby in numbers. Others are chaotic, wild, unsolvable by hand. Scientists still argue whether the hardest of these equations, especially in turbulent fluid motion, can even be solved in principle. The Navier-Stokes equation, for example, is one of the great Millennium Prize problems, still unsolved, still smug. But you don't need to solve anything right now. Just picture a dot on a curve moving gently, pulled forward by invisible rules. That's what these equations do. They trace the arc of what could happen. So as you fall deeper into thought, imagine the future not as a mystery, but as a soft, glowing curve, guided by math, shaped by motion, and unfolding one sleepy second at a time. Tonight, we drift into beauty, where numbers sculpt perfection. You're standing in front of a seashell, running your finger along its curve. The spiral winds inward with quiet precision. You see the same spiral in sunflower seeds, hurricane clouds, even galaxies. This is the realm of the golden ratio, math's most poetic obsession. Roughly 1/6, the golden ratio, often denoted by the Greek letter F, phi, shows up when the ratio of a whole to its larger part is the same as the ratio of that larger part to the smaller. It's balance, nested within balance, a kind of self-similarity that feels just right. The ancient Greeks used it in architecture. Renaissance artists used it to compose paintings. Modern designers still lean on it when crafting logos, layouts, and sometimes just vibes. Even the proportions of the Parthenon and the spirals of pine cones seem to whisper its name. And here's your quirky tidbit. Salvador Dali framed elements of his paintings using golden rectangles. When you're melting clocks onto tree branches, you might as well use divine proportions, right? But is the golden ratio really everywhere? Scientists still argue whether it's a universal law or just a very convincing pattern that we love to find. Some studies say humans are naturally drawn to it. Others call that idea mathematical pareidolia, seeing structure where there might only be coincidence. Still, the golden ratio connects to Fibonacci numbers. As the Fibonacci sequence continues, the ratio between each pair of numbers edges closer and closer to F. It's as if the golden ratio is the silent conclusion of that dreamy spiral we explored earlier. So tonight, picture a spiral gently curling in the distance, elegant, endless, symmetrical. It doesn't scream for attention. It doesn't need to. Like a lullaby wrapped in geometry, the golden ratio is just there, humming beneath beauty, offering you a perfectly measured breath. Let's roll the dice and tumble into probability's quiet little universe. You're sitting at a green felt table, 2 dice in your hand. You shake, you roll. They clatter softly. What's the chance you'll get a 7? Not bad. What about 2 6s? Trickier. Now you're not just playing, you're doing math. Sneaky, sleepy math. Probability is the study of uncertainty. It tells you how likely something is to happen, even when the world feels totally random. Every coin flip, every weather forecast, every time you ask yourself, what are the odds? You're inviting probability to whisper in your ear. Early thinkers like Pascal and Fermat used probability to solve gambling problems. It quickly evolved into a mathematical powerhouse. Now it's in medicine, finance, sports, AI, even predicting traffic patterns. If there's a decision to be made, or a chance something might go wrong, probability's probably involved. Here's your quirky tidbit. Casinos don't beat the odds. They are the odds. Every game is designed with just enough mathematical edge that, over time, the house always wins. It's not luck, it's law. Glitter-covered slot machine law. But probability isn't just about guessing. It's built on logic and structure. There are rules. The probability of an event is always between 0 and 1. All possible outcomes must add up to 1. And the more you repeat an experiment, the closer you get to its true probability. That's called the law of large numbers, where chaos becomes calm through sheer repetition. Scientists still argue about how to interpret probability. Is it a frequency, a belief, a property of nature? There's classical probability, Bayesian probability, quantum probability. Each a different philosophy, like dreamers debating how fate works in the quiet of night. So as you drift now, imagine dice spinning in slow motion, cards being dealt, raindrops falling, every tiny event laced with chance, yet governed by patterns. And in that soft uncertainty, probability hums, reminding you that even randomness has a rhythm. Tonight, we step into the fog, where statistics say one thing and the truth says, maybe. You're looking at two identical reports. Both claim to show the same data. One says eating chocolate increases lifespan. The other, that it shortens it. Welcome to the weird and wobbly world of statistical paradoxes, where numbers can lie without actually lying. Statistics is math's attempt to wrangle messy reality into something we can understand. Averages, percentages, margins of error, tools to make sense of huge amounts of information. But sometimes, those tools twist back on themselves like sleepy snakes. Take Simpson's paradox, for example. It shows how a trend in several groups of data can disappear, or even reverse, when those groups are combined. Imagine two hospitals. One has a higher success rate in surgeries for men, and the other for women. But combine the data. Suddenly, the hospital with worse individual stats looks better overall. It's like the numbers staged a mutiny. Or the Monty Hall problem, a probability puzzle involving 3 doors, a car, and 2 goats. You pick a door. 1 goat is revealed. Do you switch? The answer is yes, always switch. But it feels wrong, even though the math says you're doubling your odds. Your brain doesn't like being told it's wrong by a goat. Here's your quirky tidbit. The famous phrase lies, damned lies, and statistics was popularized by Mark Twain, though he borrowed it from someone else. Even in the 1800s, people knew that a well-placed percentage could confuse more than clarify. Scientists still argue about the best ways to interpret and communicate statistical findings. Do we prioritize simplicity or precision? Should we trust p-values, confidence intervals, or gut instinct? There's no single answer, just overlapping opinions wrapped in charts. So tonight, picture a sea of numbers shifting beneath the moonlight. They shimmer, they promise truth. But look again, and they've changed. Not because they're false, but because reality is more complex than a single average. And in that complexity, statistics rocks you gently, telling the truth, or at least one version of it. Let's tiptoe into the realm of ridiculously large numbers, the ones too big to picture, too weird to use, but too fascinating to ignore. You're holding a balloon, a nice big round number, maybe 1,000. Now blow it up, 10,000, 1,000,000. Keep going. Eventually, you hit a number called a googol, a 1 followed by 100 zeros. That's more than the number of atoms in the known universe. And it's just the warm-up act, a googolplex. That's a 1 followed by a googol of zeros. You couldn't even write it out if every atom in the universe were a pencil, and every second of time was a sheet of paper. It's not just big, it's comically big. Like, why does this exist big? But then along comes Graham's number, a number so massive it makes Googleplex look like a toddler's doodle. It was created as an upper bound for a specific problem in Ramsey theory, and it's so large we can't write it in standard notation. We can't even think it really. The last digits are known, but the full number? Not a chance. It's stored in layers of exponents stacked like infinity's Jenga tower. Here's your quirky tidbit. Graham's number was once in the Guinness Book of World Records as the largest number ever used in a serious math proof. And when physicist Carl Sagan heard about it, he said trying to visualize it would rupture your cerebellum. So don't do that. Scientists still argue what it means to use numbers like this. Are they real tools? Or are we just stretching symbols past their limits? And is there a difference between something being mathematically valid and actually useful? For now, as you float down towards sleep, imagine yourself drifting through a space so vast, numbers themselves start to blur. You pass millions, trillions, quadrillions, then beyond, into a zone where naming numbers becomes performance art, where infinity waits, and then Graham's number smirks from behind it. Tonight, let's fall into the quiet, dark mystery of nothing. 0, a circle, a whisper, a placeholder, a paradox. You've seen it a million times, but how often do you feel it? It's the symbol for nothing, and yet it changed everything. In ancient times, people didn't have 0. Early number systems counted with marks, tallies, and symbols. There was no need to represent none. If you had no sheep, you just didn't draw any. But eventually, as trade, calendars, and calculation grew more complex, people needed a symbol to stand in for absence, something that meant nothing and yet did something. 0 arrived like a quiet revolution, first in ancient India, then spreading through the Islamic world, and eventually to Europe. It wasn't just a number, it was a new way of thinking. With 0, place value became possible. Now 204 and 240 weren't just jumbles, they had structure. Suddenly, math had a backbone. But 0 is also dangerous. Try dividing by it, and your calculator just gives up. Undefined, it says, as if offended, because division by 0 isn't just wrong, it's nonsensical. How many times does nothing go into something? Your brain may already be retreating. Here's your quirky tidbit. When 0 was first introduced to Europe, it was treated with suspicion. People feared it might lead to errors, lies, or even financial fraud. Some merchants literally banned it. Imagine being afraid of a circle. Scientists still argue whether 0 is a number, a concept, or both. In physics, the idea of absolute 0 refers to the coldest possible temperature, where particles stop moving. But can something ever truly be nothing? Or is 0 just the shadow of something that's not there? So as you drift into silence, let 0 be your companion. Not empty, not blank, just still. The place where everything pauses. The breath between thoughts. A soft, invisible foundation holding the whole structure up. Let's gaze into the mirror now, where math reflects itself in perfect balance. You're in a quiet hallway lined with mirrors. Step forward, and your reflection steps too. Hold up one hand, and it matches you, but reversed. This is symmetry, the calm heartbeat beneath much of mathematics, nature, and even your dreams. In math, symmetry means balance. An object is symmetrical if flipping, rotating, or shifting. It leaves it looking the same. A butterfly, a snowflake, a heart drawn just right. Symmetry isn't just pretty, it's powerful. It tells you a shape's secrets without needing to measure every side. It reveals the rules the universe might be following behind the scenes. There are different kinds. Reflectional symmetry, like a folded paper snowflake. Rotational symmetry, like a wheel. And translational symmetry, like tiles repeating across a floor. Each one whispers a different pattern. Together, they form math's soft language of elegance. Here's your quirky tidbit. Your own body is mostly symmetrical. 2 eyes, 2 ears, 2 arms, but not quite. Most people's left and right sides aren't identical. You might even have one eyebrow that always looks more expressive. It's nature's little asymmetrical joke. And symmetry isn't just pretty fluff. In physics, it underpins laws of motion and conservation. Emmy Noether, a brilliant mathematician, whose name you should absolutely know, proved that every symmetry in physics corresponds to a conservation law. Time symmetry conserves energy. Spatial symmetry conserves momentum. It's like the universe rewards balance with stability. Scientists still argue whether the universe is fundamentally symmetrical or just pretending to be. Some think the Big Bang broke a perfect symmetry, leaving us with a slightly lopsided cosmos. Others think deeper, hidden symmetries still guide the entire structure. So tonight, picture yourself reflected not just in glass, but in equations, in spirals, in galaxies. Perfectly balanced, but still uniquely you. Symmetry doesn't erase difference. It cradles it gently in repetition, rhythm, and quiet pattern. And as your thoughts slow, you begin to feel it. Not everything has to change. Some things, like symmetry, just stay, steady and silent as you drift away. Now step softly into the shadows, where chaos hides just beneath the calm. You're watching a pendulum swing, back and forth, predictable, peaceful. But now imagine the string is stretchy, the weight is sensitive, and the system gets nudged, just a little. Suddenly, it's no longer gentle. It's darting, tumbling, flipping in ways you can't predict. Welcome to chaos theory, where small changes create big, beautiful messes. Chaos theory doesn't mean total randomness. It means sensitive dependence on initial conditions. Change the starting point by a hair, and you end up somewhere totally different. This is often called the butterfly effect, where a butterfly flapping its wings in Brazil might influence a tornado in Texas. Sounds poetic, and it kind of is. Here's the strange part. Chaotic systems still follow rules. The equations are clear, often simple, but their behavior spirals so wildly that prediction becomes impossible. Weather systems, stock markets, populations, your morning mood, all complex, all chaotic in their own twitchy little ways. And yet, inside that chaos, patterns emerge. Strange attractors, beautiful loops in space that never repeat, but never stray. Fractals appear, symmetry flickers, even disorder carries echoes of order. Here's your quirky tidbit. The famous Lorentz attractor, the swirling shape that defines chaos, was discovered by a meteorologist who was just trying to save time. He rounded some numbers off to rerun a weather simulation. The outcome? Totally different. Chaos, it turns out, hates shortcuts. Scientists still argue whether chaos is a feature of nature or a flaw in our ability to measure it. If we had perfect knowledge of every molecule in the sky, could we predict the next storm? Or would the universe still slip out from under our calculations, laughing softly? So as you rest now, imagine your thoughts like ripples in a pond. A small idea, a passing feeling. each one branching into 1,000 possibilities. Beautiful, unrepeatable, not broken, just complex. You don't have to predict every wave. Just let them move. Let's wander into the minds that dared to prove the impossible. You're walking through a candle-lit library, shelves lined not with books, but with proofs. Each one a delicate thread of logic, stitched from assumption to conclusion. Some are elegant, others rough around the edges, but a few broke brains. Proofs are the lifeblood of math. They're not guesses or experiments. They're airtight arguments that something is true, not just today, but always, forever. Once something is proven, it can't be unproven. It's like math carving a fact into the bedrock of reality. But not all proofs are friendly. Some are strange little beasts that twist expectations. Take the Banach-Tarski paradox. It claims you can take a solid ball, cut it into 5 pieces, using some very unhelpful math tools, and reassemble those into 2 identical balls. No shrinking, no stretching, just duplication. Your brain might file this under nope, but mathematically, it checks out. Just don't try it with an actual basketball. Then there's the proof without words. Simple diagrams that demonstrate truth visually, like a triangle inside a square, quietly revealing the Pythagorean theorem without saying a single thing. Math, but whispered. Here's your quirky tidbit. Paul Erdős, one of the most prolific mathematicians ever, believed that every perfect proof came from a mythical place he called the book, a celestial volume in which God kept the most elegant versions of every mathematical truth. He spent his life chasing those proofs. Scientists still argue about what makes a good proof. Is it simplicity, rigor, surprise? Some proofs span hundreds of pages. Others fit on a napkin. Some are elegant. Others are so technical they make mathematicians cry, literally. So as you drift now, picture yourself weaving through corridors of logic, where every turn has a purpose. No guessing, no assumptions, just steps leading toward clarity. A perfect little path from the unknown to the known, quiet, unshakable, and true. Let's fold the universe just a little and see what shapes appear. You're holding a piece of paper. It's blank, harmless, but fold it once, then again and again. And suddenly, it's no longer simple. It's become a shape, a structure, a form with tension, intention, and believe it or not, mathematics. Welcome to the world where origami meets higher dimensions. This isn't just arts and crafts. It's geometry in motion. Each crease you make becomes a line, an angle, a transformation. Origami is math folded into reality. Engineers study how paper folds to build collapsible structures, from satellite panels to stents in heart surgery. Mathematicians model the folds with algorithms, treating each corner like a point on a map. With the right rules, you can fold nearly anything. Frogs, flowers, even spheres. But things get stranger when you move beyond 3 dimensions. In higher dimensional spaces, folding works differently. Imagine taking a cube and unfolding it into 2-dimensional nets. Now imagine 4-dimensional cubes, called tesseracts, casting 3-dimensional shadows. The folds get weirder, more dreamlike. Geometry starts speaking in riddles. Here's your quirky tidbit. NASA used origami-inspired designs to fold large telescope mirrors and solar arrays into rockets. When deployed, they unfold smoothly, like a space ballet choreographed by math. Scientists still argue how to best visualize these higher dimensions. We can't see them directly, but with math, we can model their behavior. It's like glimpsing part of a larger truth through a half-open door. So tonight, As your thoughts soften, picture folding your mind like paper. One crease for memory, another for dreams. A tiny mountain fold for that thing you forgot to do today. It's okay. Fold again. You don't have to understand every dimension. You're already part of one. Just feel the shapes forming, gently, layer by layer. You're not just observing math, you're inside it. Fold it in. Let's pull out a crumpled old map and use it to break math. You're standing in front of a coloring book filled with tangled countries, twisty coastlines, and awkward borders. Now imagine this. No matter how complex the map, you can color every region using just 4 colors, so that no 2 touching areas share the same color. Seems random. Sounds like a party trick, but it's one of the weirdest and most hard-earned truths in mathematics. This is the 4-color theorem. It says that 4 colors are enough to color any map on a flat surface. That's it. Simple statement. But proving it? Not so simple. Mathematicians tried for over 100 years. Dozens of brilliant minds chipped away at it. In 1906, 2 researchers, Appel and Harkin, finally cracked it. But here's the catch. Their proof relied heavily on a computer. It checked thousands of configurations, one by one. It worked, but many mathematicians weren't happy. "If you can't follow the logic with a pencil," they whispered, "is it really a proof?" Here's your quirky tidbit. The 4-color theorem was the first major mathematical theorem to be proven using a computer. It marked a turning point, when human thought teamed up with machine endurance. And not everyone agreed that was a good thing. Scientists still argue about the philosophical side of it. Can a proof be trusted if no human has read every line? Or is that just pride talking? Some say the theorem feels like a riddle that was brute forced open. Others say it's beautiful, a testament to teamwork between brains and circuits. And maps aren't just borders, they're graphs. Every region is a node. Every shared border is a connection. Graph theory grew alongside this problem, blossoming into one of math's most exciting fields. So tonight, imagine a world drawn in looping borders, swirling regions, and softly blending shades. 4 colors, always enough. No matter how messy the world gets, there's a calm rule beneath it. You don't have to solve it. Just know that even the most chaotic maps can be tamed with a handful of crayons. Now take one careful step into dust so fine you can't even see it. You're floating over a line. At first glance, it looks like just a line. But as you zoom in, something strange happens. You see tiny dots, isolated, floating, never touching. No matter how far you zoom, you never find a segment, just more dust. This is Cantor's dust, a haunting little construction in the world of set theory. Named after Georg Cantor, the same man who showed us there are infinities larger than other infinities. This dust is what's left when you systematically remove the middle third of a line segment over and over and over. First you remove the middle third, then the middle third of the pieces that remain, then again and again. Soon you have a set made entirely of gaps. But weirdly, there's still something left. The Cantor set is uncountably infinite, yet it has a total length of 0. That's like having an infinite number of thoughts that somehow take up no space in your brain. It's a paradox in motion, a ghost made of math. Here's your quirky tidbit. Cantor didn't just discover new kinds of sets, he also suffered greatly for them. Many mathematicians rejected his ideas, and he was frequently dismissed by his peers. Despite his brilliance, He spent long periods battling depression in mental institutions. The infinities he explored were beautiful and brutal. Scientists still argue about the implications of these strange sets. Are they just theoretical playgrounds? Or do they have hidden connections to real-world physics? Some even appear in studies of chaos theory, quantum structures, and fractal geometry. So tonight, imagine drifting through a space that seems solid until you look closer. It's not empty. It's not whole. It's something in between. A space full of invisible points gently resisting your touch. Cantor's dust doesn't blow away. It simply is, still, infinite, weightless, and as you exhale, imagine your own thoughts becoming light as dust, quiet, scattered, and infinite in their own small way. Let's wander into the grey space between yes and no. You're standing at a switch. Flip it up, on. Flip it down, off, simple, clean, binary. But what if the switch is halfway, not quite on, not quite off, just hovering? Welcome to fuzzy logic, where truth comes in shades, not absolutes. Classical logic, the kind you meet in school, demands crisp answers. A statement is either true or false, 1 or 0. But fuzzy logic says, let's not rush. Maybe something is partly true, or mostly false, or 72% likely to be your next late-night fridge decision. Fuzzy logic was introduced in the 1960s by Lotfi-Zadeh, a mathematician who realized that the real world is a little blurrier than textbook logic allows. Things aren't always black or white. Sometimes the answer is meh. Here's your quirky tidbit. Washing machines in Japan use fuzzy logic. They sense how dirty your clothes are and adjust water levels and timing accordingly. Not based on strict rules, but based on a soft web of kind of and probably and almost. Even your laundry gets math. In fuzzy logic, truth values range from 0 to 1, sliding smoothly across the scale. It's a way to model real-world thinking, how humans make decisions without crisp rules. Should you go outside? It's kind of cloudy. Are you hungry? Sort of. Will you finish this chapter? Maybe. Scientists still argue about the role of fuzzy logic versus probabilistic reasoning. Is fuzziness just probability in disguise? Or is it its own unique beast? A model of uncertainty without randomness. So as you fall deeper into thought, picture yourself walking a path made of maybe, not yes, not no, just gentle degrees of almost. The world isn't binary. It's a soft watercolor of truth, fading from one possibility to another. And in that space, somewhere between on and off, between logic and intuition, you find a quiet place to rest, undefined, unbothered, gently fuzzy. Step into the orchestra pit of the universe, where math plays in harmony. You're looking at a snowflake, 6 arms perfectly balanced. Or maybe you're watching dancers rotate in unison. There's something underneath, holding it all together. A hidden rhythm, a structure. This is group theory. The mathematics of symmetry. A group in math isn't a crowd. It's a set of elements combined with an operation, like addition or rotation, that follows a few clean rules. Closure, identity, inverses, and associativity. If that sounds formal, don't worry. You've seen groups everywhere. They describe the way a square rotates, the way a Rubik's Cube twists, even the way molecules spin in space. Every time you rotate a snowflake or flip a shape and it looks the same, that's a symmetry. And every symmetry belongs to a group. Together, These groups form a quiet skeleton behind beauty. They organize chaos, like a conductor keeping time while the math plays its tune. Here's your quirky tidbit. In the 1800s, Évariste Galois used group theory to solve the age-old question of which equations can be solved neatly and which cannot. He proved some roots are ungettable. Then he died in a duel at 20, after writing his final math thoughts in a flurry the night before. Because of course he did. Group theory doesn't stop at snowflakes and drama. It forms the foundation of modern algebra, particle physics, cryptography, and more. The standard model in physics, built on symmetry groups, your phone's encryption, also group theory. Scientists still argue over whether the universe is made of symmetry, or whether we just use it to make sense of what we see. Either way, symmetry helps us decode complexity, like finding a melody inside a mess of sound. So tonight, imagine you're part of a pattern. You shift slightly, flip, rotate, and still feel like yourself. The world may change, but some deep part of you remains balanced. That's the power of groups. Quiet, precise, unshakable. And as you breathe out, feel that structure holding you, like a mathematical lullaby, repeating softly in the background. Now dim the lights and listen to the language of certainty. You're in a small room with two doors. One leads to treasure, the other to a rubber chicken. A sign on the wall says, if the treasure is behind door A, then this sign is telling the truth. Suddenly, you're in the realm of symbolic logic, where math and meaning swirl together, in gentle, structured confusion. Symbolic logic takes everyday ideas, if this, then that, and turns them into clean symbols. It's the blueprint beneath reasoning, the foundation of all proofs, algorithms, and yes, even your AI assistant. You start with propositions, statements that are either true or false. From there, you build with logical operators, and or not, if or then. These aren't just abstract doodles. They form truth tables, proofs, and entire systems of knowledge. The phrase, if it rains, then the ground gets wet, becomes a tidy formula. And suddenly, your messy world of weather forecasts and wet socks becomes navigable. Here's your quirky tidbit. George Boole, one of the pioneers of symbolic logic, developed Boolean algebra, an entire system using just true and false values. Today, that system underlies every digital device. Every bit, every byte, every Hey Siri, built on Boole's crisp little logic gates. Symbolic logic also powers mathematics itself. We use it to prove theorems, construct algorithms, and verify that what we think is true really is. It's the language math uses when it wants to be absolutely sure. Scientists still argue about the limits of logic. Can everything be reduced to symbols? Can truth exist outside logic? Gödel's incompleteness theorem, which we'll visit later, suggested that some truths can't be proven within the very system trying to prove them. Logic, it turns out, has boundaries. So tonight, as your thoughts slow down, imagine statements floating past like stars. Some flicker true, others dim into false. And between them, elegant symbols connect their meanings, forming a soft web of understanding. You don't need to decide which door to open. Just enjoy the structure, the calm, the clarity, the quiet rhythm of thought itself. Let's lace up your imaginary shoes. We're going knot hunting in higher dimensions. You're holding a piece of string. You tie it into a loop, then you twist it, tangle it, tug at it, and realize that even something this simple can become a mathematical mystery. Welcome to knot theory, a strange corner of topology where shoelaces, headphones, and DNA all get the spotlight. In knot theory, a knot isn't a messy shoelace. It's a closed loop, no loose ends, just an elegant twist of space floating forever. Two knots are considered the same if you can transform one into the other without cutting or gluing. Just gentle, dreamlike manipulations. But things get tricky fast. There are prime knots, the simplest kinds, and composite knots, which are like combining two knots into one. There's a whole classification system for knots, some with charming names like the trefoil, the granny knot, or the figure eight. You could get lost in their curls forever. Here's your quirky tidbit. Mathematicians use polynomial expressions, yes, actual equations, to identify different knots. It's like assigning each knot its own secret mathematical name tag. Your tangled earbuds, they might be a 74 knot on a bad day. Now picture moving this knot into 2 dimensions. Flat, impossible to tangle. That's the curse of lower dimensions. You can't make real knots in them. In 1 dimension, your string just passes through itself. In 2, it lies flat. You need at least 3 dimensions to make a proper mess. And it gets weirder in 4, where knots can sometimes untie themselves. Yeah. It's like the universe suddenly says, nah, that loop? Not a problem anymore. Scientists still argue about how knot theory applies to real-world phenomena. Physicists explore knotted particles and twisted fields. Biologists study knotted proteins and DNA strands. Even quantum computing flirts with knot logic, searching for structure in entangled states. So as you fall deeper into thought, imagine tracing a string through space, looping softly, no beginning, no end. Not stuck, not tangled, just endlessly twisting in ways that only dreams, or topology, can understand. Now let's walk across some bridges and break math in the process. You're standing in the 1700s in a sleepy little town called Königsberg. It's split by a river with 7 charming bridges connecting its parts. Locals dare each other to walk across each bridge once and only once without repeating. Everyone fails. Enter Leonhard Euler, who looks at the problem and says, let's stop thinking like pedestrians. Let's think like mathematicians. This is the birth of graph theory. Euler realized it didn't matter what the land looked like, just the connections. He stripped the problem down to dots, called nodes, for land masses and lines, edges, for bridges. With that, the modern idea of a graph was born. Not a bar chart, but a structure of relationships. Dots and lines, pure connection. And the result? It's impossible. You can't walk all 7 bridges exactly once. Euler proved it, simply and beautifully. A legend was born, and a whole new field of math unfurled from a riverside stroll. Here's your quirky tidbit. Graph theory now powers almost everything. Social networks, web searches, road systems. Your favorite streaming service uses graphs to figure out what you might like next. Euler's lazy river walk turned into the blueprint for the internet. Graphs can be simple, 2 dots connected by a line, or wildly complex, with thousands of nodes and tangled edges. There are cycles, trees, paths, and cliques. Some graphs are fully connected. Others are just awkward acquaintances. And beneath them all lies a quiet logic. Who connects to whom and how? Scientists still argue about the deep properties of graphs. How to find the shortest path, the most efficient network, the most influential node. Entire algorithms, like Dijkstra's or PageRank, were born to answer those questions. So as you drift now, picture the bridges in your own mind. Thoughts as nodes, Memories as edges, all softly connected. Some paths repeat, some fade, but together they form the beautiful graph of you. Euler didn't just solve a puzzle. He taught us to see structure in chaos. And tonight, that structure is your lullaby. Now let's chase an ancient impossibility, quietly, under the moonlight. You're sitting with a compass and straightedge, drawing perfect circles and flawless lines. The air smells of parchment and problem solving. Your goal? Simple. Take a circle and draw a square with the exact same area. No measuring, no guessing, just pure geometry. This is the infamous challenge of squaring the circle. For thousands of years, this problem teased mathematicians. The Greeks tried, the Indians tried, Renaissance minds tried. Everyone believed it was possible. It just had to be. After all, how hard could it be to turn roundness into squareness? But the universe had other plans. At the heart of the problem lies pi, that irrational, unending, beautifully messy number. You need p to find the area of a circle. But to square that same area with just a compass and straightedge, you'd have to construct p. And that, it turns out, is impossible. In 1882, mathematician Ferdinand von Lindemann proved p is transcendental, not just irrational, but totally untouchable by algebraic means. It cannot be the root of any polynomial equation with rational coefficients. That one proof crushed 2,000 years of hope like a dropped chalk stick. Here's your quirky tidbit. Despite being proven impossible, artists and amateur enthusiasts still try to square the circle. They know it can't work. But the act itself, trying anyway, has become a kind of poetic math ritual. Scientists still argue about the emotional legacy of problems like this. Are they tragedies or triumphs of knowledge? Some impossibilities, after all, reveal deeper truths than any success could. So as you curl deeper into your blanket, imagine your thoughts tracing soft curves, circles, squares, endless attempts to match their souls. You don't need to succeed, you just need to try, quietly, gracefully, forever. And in that impossible act, you've joined a lineage of dreamers, compass in hand, eyes full of wonder, still squaring, still circling. Let's weigh the impossible without moving a muscle. You're standing in a meadow, surrounded by invisible forces. There's a balloon tied to your wrist, a breeze nudging it upward. You want it to stay still, right where it is, not flying, not falling. Balanced. That's the heart of optimization, finding the best possible outcome within given constraints. And when the problem gets tricky, when your balloon is tied to multiple poles or drifting over uneven terrain, you turn to a tool called Lagrange multipliers, a fancy name for a powerful idea. How to find the maximum or minimum value of something when there are limits you can't ignore. Let's say you're hiking and trying to reach the highest point on a slope, but you're only allowed to stay on a narrow path. Lagrange multipliers help you find that peak within your path. They say, you want to go up, but you're tied to this curve. So here's the highest you can get without snapping the rope. It sounds abstract, but it's used everywhere. Economics, engineering, machine learning, even airline scheduling. Anytime you need to optimize something with rules, cost with a budget, volume with a shape, happiness with time, this method quietly steps in. Here's your quirky tidbit. Joseph Louis Lagrange, the mathematician who gave us this trick, once reorganized Newton's mechanics into pure rule-based elegance, without using any diagrams, just letters, symbols, and sleepy brilliance. Scientists still argue whether optimization problems reflect how nature truly works, or if we just project our obsession with efficiency onto the universe. Is everything really trying to optimize, or is that just a math-flavored illusion? So tonight, imagine yourself floating between two gentle forces, one pulling, one holding back. You don't fight it. You don't need to. You're at your perfect point, the best balance you can reach within your world. Not infinite, not ideal, but just right for you. That's optimization. Not perfection, but peace under constraint. Now we enter a space where perspective takes over, where geometry loosens its tie and gets a little abstract. Imagine standing at the end of a long, straight road. The lines on either side stretch to the horizon until, wait a minute, they meet. That's projective geometry, where parallel lines aren't actually parallel. They just haven't had their big reunion yet. Projective geometry is what happens when you take regular geometry and toss in the idea of points at infinity. In this dreamy framework, all lines eventually intersect. If not in your field of vision, then somewhere out there in the mathematical mist. It's less about distance and more about relationships. Perspective, proportion, angles, yes, but in a softer, stretchier way. Artists figured this out long before mathematicians did. Renaissance painters like Leonardo da Vinci were secretly doing projective geometry when they sketched tiled floors and cityscapes that pulled your gaze to a vanishing point. They didn't just draw, they bent space to their will. Here's your quirky tidbit. Projective geometry plays a major role in computer graphics, 3D modeling, and even your phone's camera. Every time you take a portrait in portrait mode, and the background blurs just right, that's projective math, smoothing the illusion. And it doesn't stop with perspective. Projective geometry connects deeply with conic sections, circles, ellipses, parabolas. It even shows up in relativity, where the way space and time warp depends on your viewpoint. It's the geometry of shadows, of projection, of what things look like when you can't quite see the whole picture. Scientists still argue whether projective space reflects physical reality or is just a useful abstraction. Either way, it offers a powerful reminder. How you look at something can completely change what you see. So tonight, imagine lines stretching endlessly across your mind. Some meet, some fade, some bend into curves. But in projective geometry, none are truly alone. Everything connects, eventually. Even the parallel lines that swore they'd never see each other again. Now let's revisit a classic math nightmare. Only this time, it's wearing pajamas. You open your eyes and find yourself back in school. A clock ticks. The fluorescent lights hum. A piece of paper lands on your desk. It's a word problem. And somewhere deep in your soul, you sigh. But tonight, there's no pressure. Just a chance to stroll through one of math's most misunderstood rituals. Word problems are like little stories dressed in algebra's clothing. If train A leaves the station going 60 miles per hour, you know the drill. The goal is to take language, messy, vague, human language I gauge, and translate it into numbers, equations, and clarity. It's not just about solving, it's about decoding. Why are they so tricky? Because they blend logic with literacy. You need to understand what's being said and what's being asked. It's like math trying to be a detective novel with fewer plot twists and more decimals. Here's your quirky tidbit. Word problems go all the way back to ancient Babylon. One old tablet includes a problem about buying and selling barley. It ends with, essentially, figure out how much silver you're getting ripped off for. So if you've ever felt betrayed by a math question, you're not alone. It's a 4,000-year tradition. Scientists and educators still argue about how best to teach them. Should we simplify the language, add visuals, turn every problem into a relatable story about pizza? Maybe. Or maybe the challenge is the point, turning words into logic, language into structure, confusion into something solvable. So tonight, picture a word problem unfolding slowly like a bedtime fable. A fox and a rabbit share a trail. A gardener plants rows of vegetables in a sleepy spiral. A ladder leans against a dreamlike wall. No pressure, no time limit, just stories waiting to be solved. One quiet sentence at a time. And in this version, the trains don't collide. They just pass each other gently in the moonlight. Let's step into a place where 1 + 1 doesn't always equal 2, and nobody's panicking. You're looking at a clock. It's 11 o'clock. You add 2 hours. The answer? Not 13. It's 1. Time just wrapped around. You've entered the land of modular arithmetic, where numbers loop instead of stretching forever. In this system, we say things like 13 1 mod 12, which is a fancy way of saying that after going 12 steps forward, we loop back to 0. It's like math with a curfew. Once the number gets too big, it quietly sneaks back to the beginning. Modular arithmetic is often called clock arithmetic for a reason. Time is a perfect example. Days of the week, months of the year. Even musical notes repeat in cycles. The world turns and math turns with it. But this isn't just a quirky trick. Modular math underpins cryptography, the stuff that protects your texts, your credit card info, even this very video. It also appears in patterns, computer science, number theory, and puzzles like Sudoku. Here's your quirky tidbit. The legendary mathematician Carl Friedrich Gauss introduced modular arithmetic when he was still a teenager. He treated numbers like loops on a circle and revolutionized number theory in the process. Just your average 18-year-old move. Scientists still argue about the deeper implications of modular systems. Why does the universe seem to love cycles so much? Is modularity a quirk of human math, or a reflection of something truly fundamental? So tonight, picture a line of numbers that curls back on itself like a sleepy snake. Every step forward brings you closer to a familiar place. There are no ends here, just beginnings wrapped in circles. And suddenly, 1 + 1 = 2, until it doesn't. And that's okay. You're not breaking math. You're just shifting perspective. A number isn't wrong just because it loops. It's just taking the scenic route home. Now let's slip into something elegant, compact, beautiful, and quietly mind-blowing. You're standing at the crossroads of 5 numbers, not random ones, but the 5 most famous in all of math: 0, 1, P, E, and I. And suddenly, they all appear in one short equation, like the cast of a movie showing up in a single scene. This is Euler's identity, often called the most beautiful formula in mathematics. Don't worry, we won't say it out loud. We're here to feel it. This tiny equation weaves together exponential growth, imaginary numbers, the circle, unity, and nothingness. It takes concepts from calculus, geometry, and complex analysis and ties them into a single, whisper-quiet sentence. It's as if the universe briefly paused to sign its name. Leonhard Euler, the Swiss mathematician behind this marvel, didn't invent any of the pieces alone, but he's the one who saw how they connected, like a poet writing the cleanest possible haiku with numbers. Here's your quirky tidbit. Euler himself never actually called this identity beautiful. but generations of mathematicians have swooned over it. Some call it math's Mona Lisa. Others say it feels like a secret wink from the cosmos. Scientists still argue whether mathematical beauty is real, an objective truth, or just something we project onto symbols that feel satisfying. But when formulas like this appear, connecting concepts that should never have met, it's hard not to feel a little awe. So as you drift deeper into sleep, imagine those 5 numbers standing quietly in a circle. They nod to each other, they align, and then they balance out in perfect silence, each playing its role, each stepping back into the night. It's not just an equation. It's a lullaby written in the language of the universe. Now we move behind the curtain, where numbers vanish on purpose. You're in a dimly lit room surrounded by whispers, not voices, data. It's being encrypted, masked, locked away. But how? With math. Specifically, with the dreamy art of cryptography, where equations act like spies and secrets wear armor. At the heart of modern cryptography is something called modular arithmetic. Yes, the clock math we just explored. And prime numbers, very large ones. When you multiply 2 giant primes together, the result is easy to get. But if someone only sees the result and tries to figure out the original primes, that's hard, really hard. Like, take longer than the universe's lifespan hard. That's the trick. And it's what keeps your bank account safe, your messages private, your online shopping unembarrassing. One of the most famous encryption systems is called RSA. Named after its inventors, it builds an encryption key using primes, then uses clever math to scramble data. Anyone can lock a message using the key, but only someone with the private key can unlock it. Here's your quirky tidbit. Julius Caesar used a primitive version of cryptography called the Caesar cipher. He'd just shift every letter a few steps forward in the alphabet. A became D, B became E, and so on. Not exactly Fort Knox, but it worked for him. Scientists still argue about the future of cryptography. Quantum computers, if perfected, could break today's encryption in minutes. So now researchers are racing to develop post-quantum methods, math designed to withstand the computing power of tomorrow. But tonight, there's no rush. Just imagine your thoughts slipping into code, gently scrambled, softly secured. You're not hiding anything sinister. You're just tucking your ideas in, keeping them safe in a velvet envelope of math. Because sometimes, the most beautiful part of a number is how it disappears. Now let's step inside the code of reality itself, into the quiet, ordered world of linear algebra. You find yourself on a glowing grid. Each step you take shifts you perfectly to a new position. Left, right, up, down. Everything moves smoothly, predictably. This isn't a game board. It's a matrix, and you're inside it. Linear algebra is the math of grids, vectors, and transformations. It describes how things move, stretch, rotate, and shift in space. It's not about solving for x anymore. It's about systems of variables all interacting together. It's like going from a solo performance to an orchestra. A matrix is just a rectangular array of numbers. But it can do amazing things. Rotate a 3D object, stretch a shape, project shadows, translate data from one form to another. Vectors, little arrows, fly through this space, and matrices push them around like invisible hands. Here's your quirky tidbit. In the 1999 movie, The Matrix, the green cascading code is actually sushi recipes written in Japanese. But the deeper metaphor of being trapped inside a mathematical grid, that's pure linear algebra. The Matrix wasn't just cool sci-fi. It was quietly mathematical. And this math runs everything. Computer graphics, machine learning, quantum mechanics. Even Google's search algorithm relies on a form of matrix analysis called PageRank. When you move through the internet, you're walking through invisible vector spaces. Scientists still argue about how intuitive linear algebra really is. Some say it's abstract. Others say it's the most natural way to describe reality, more fundamental than calculus. One thing's for sure, it scales. From tiny robots to galaxies, linear algebra makes complexity manageable. So tonight, imagine yourself floating on a grid. Every point, every movement, described by a quiet equation. You're not lost. You're located, oriented, transformed gently by math you can't see but always feel. Because here, in the world of linear algebra, nothing is random. Every move means something, and you're part of the system. Now let's peel back the veil and peek into dimensions you can't even picture. You're standing in a cube. You know what a cube feels like. 6 faces, 8 corners, right angles. But now imagine pulling it outward in a direction that doesn't exist. A 4th spatial dimension. Congratulations, you've just built a hypercube. This isn't science fiction. It's higher dimensional geometry, where shapes evolve into forms your brain was never built to visualize. A point is 0-dimensional. A line is 1. A square, 2. A cube, 3. But go one step further, and you get a tesseract, a 4-dimensional cube. We can't draw it perfectly, but math doesn't care. It can define it, rotate it, and play with it like putty. Here's a quirky tidbit. Salvador Dali painted Christ on a tesseract-shaped cross in his surrealist piece Corpus Hypercubus. And Marvel's tesseract? Probably not what Euclid had in mind, but it does sound cooler than 4-dimensional box. Higher dimensions help in surprising places. Physicists use them to describe the fabric of space-time. Data scientists use them to represent complex information. Imagine every feature in a spreadsheet as its own axis. Suddenly, your data is floating in a 97-dimensional space. Wild. Scientists still argue whether extra dimensions are real or just convenient tools. String theory, one of the leading ideas in theoretical physics, suggests the universe might have 10 or 11 dimensions. Most of them curled up so tightly we'll never notice. But they may still influence everything, from particle behavior to cosmic structure. So as you drift now, imagine your thoughts like points, each one stretching into new directions. Not left, not right, but somewhere else. You're not trapped in 3D. You're brushing up against more. Spaces beyond sight. Shapes beyond shape. It's okay if it doesn't make sense. That's the beauty. You're dreaming in 4 dimensions now. Now let's step into a garden of symmetry, where patterns repeat, and the world tessellates softly around you. You're lying on a tiled floor. But these aren't ordinary tiles. They stretch out forever. No gaps, no overlaps, fitting together like the whispers of a dream. You've entered the land of tessellations, patterns that cover a surface completely with no cracks in between. Squares can do it, triangles, hexagons, regular shapes that tile the world with quiet precision. But then things get strange. What about shapes that don't repeat regularly? What if you could tile a floor infinitely without ever repeating the same pattern? That's where Penrose tilings come in, named after mathematician Roger Penrose. These use just 2 oddly shaped tiles to create an infinite, non-repeating pattern. It's called aperiodic, and it looks like a cosmic jigsaw puzzle that never loops, and yet it fills the plane perfectly. Here's your quirky tidbit. A Penrose tiling once showed up on the floor of a shopping center in Germany. Mathematicians saw it and gasped. The tiling had been copied accidentally, purely for aesthetic reasons. Turns out, sometimes math is so beautiful, it sneaks into interior design. Tessellations aren't just pretty. They help us understand symmetry, group theory, and even the structure of crystals. In biology, they show up in honeycombs and turtle shells. In art, think of M.C. Escher, who used tessellations to morph birds into fish, space into form, dreams into geometry. Scientists still argue about how deep these patterns go. Are tessellations just convenient visual tricks, or do they reveal a mathematical fingerprint in the fabric of reality, something primal and eternal? So tonight, imagine the surface of your mind slowly tiling itself. Each thought a shape, each shape fitting softly next to the last. You're not falling apart. You're tessellating, quietly locking into place with every breath. The pattern may never repeat, but it will always fit. Let's slip quietly into a world where math feels more like music, where abstract symbols hum with emotion. You're floating in a space made of patterns, not numbers, not graphs, just rules, relationships, structure. Welcome to abstract algebra, where math zooms out and starts asking, what happens if we don't care what the numbers are, just how they behave? Here we study things called groups, rings and fields. These aren't playgrounds or pastures. They're mathematical universes built on sets and operations. In a group, for instance, every element combines with every other in a rule-bound way. It's like a tiny society where every citizen follows the same social contract. You've met these before without realizing. Adding whole numbers, that's a group. Rotating a square, also a group. Solving a Rubik's Cube, deep in group territory. But abstract algebra asks, what happens when we remove the familiar? What if we forget what 2 or 5 even means, and just explore how things interact? It sounds cold, but there's a strange comfort in it, like knowing that no matter what world you're in, if the rules are fair, the math still sings. Here's your quirky tidbit. In Galois theory, one of abstract algebra's shining stars, you can actually use group theory to prove that certain equations can't be solved by radicals. It's math telling you, hey, stop trying. That puzzle literally has no solution using square roots. Brutal, but honest. Scientists still argue whether abstract algebra is too abstract for beginners, or whether it's the key to unlocking the deepest layers of math early on. Some say it should be taught like a philosophy course. Others say it's best whispered, like a secret. So as you float now, picture symbols dancing, not numbers, not shapes, just interactions, echoes, patterns that unfold, not because they must, but because they can. You're not solving anything tonight. You're just listening. And abstract algebra? It's the sound of math thinking about itself. Tonight, let's meet the numbers that don't play by anyone's rules, not even maths. You're walking through a garden of numbers. Rationals wave politely. Fractions like 1/2, 3/4. Even whole numbers in disguise. But then you notice some strange guests loitering in the mist. One has a symbol of P tattooed on its arm. Another hums in powers of E. These are the transcendental numbers, and they don't fit in anywhere. Unlike rational numbers or even irrational ones, like the square root of 2, transcendental numbers can't be roots of any algebraic equation with whole number coefficients. In other words, they transcend algebra itself. No polynomial can trap them. No formula can summon them cleanly. They're math's uncatchable ghosts. The most famous transcendental numbers, P and E. We've met them already, P in circles, E in growth. But we often forget how slippery they really are. They look like constants. They act like constants. But their digits go on forever without repeating, without pattern, without apology. Here's your quirky tidbit. In 1882, Ferdinand von Lindemann proved P0 was transcendental, thereby slamming the final door on squaring the circle. For centuries, geometers had tried to construct a square with the same area as a circle using only a compass and straightedge. Lindemann's proof said, nope, never gonna happen. Scientists still argue how to find other transcendental numbers. We know they exist, an uncountably infinite number of them. But explicit examples are rare. Most are like stars behind clouds, present but unnamed. And unlike integers or primes, transcendental numbers don't like community. They don't form neat groups. They don't behave predictably. They float through number theory like mathematical ghosts, real but untouchable. So as you fall into sleep, imagine yourself drifting beside one of them. Not circling, not solving, just observing. A number that slips through every net, that dances past every formula. Some things in math, like in life, refuse to be reduced, and maybe that's what makes them beautiful. Now let's enter the dream state of calculus, where change becomes a whisper and curves breathe gently beneath your feet. You're standing on a hill, not a steep one, just a soft curve under your toes. You wonder, how steep is this exact spot? That quiet question opens the door to derivatives, the magical heart of differential calculus. Derivatives measure change, how fast your car is speeding up, how the temperature shifts hour by hour, how a leaf falls faster, slower, then still. The derivative doesn't just say what is, it tells you what's happening next. To find it, you take a function and slice it thinner and thinner, zooming in until the curve looks like a line. The slope of that tiny line, that's your derivative. The math of the infinitely small. It's like asking a curve, very politely, hey, what are you trying to do right now? Here's your quirky tidbit. When calculus was first developed, it was like inventing magic. Newton and Leibniz both claimed the discovery, sparking one of history's nerdiest feuds. Today, we use both of their notations. Because why choose sides in a centuries-old math drama? Derivatives show up everywhere. In physics, to describe motion. In economics, to track marginal costs. In biology, to model how populations grow or shrink. Even the pitch of your voice when you sigh, up or down, that's a derivative in action. Scientists still argue about how to teach calculus. Should it start with limits and rigor, or jump into real-world examples, letting intuition lead? Either way, the derivative remains one of the most powerful tools we've ever made. So tonight, as your breath slows, imagine a curve under your pillow, smooth, continuous, endlessly gentle. At every point, it tells a secret, how fast things are changing. It's not loud, not dramatic, just soft clues about tomorrow, hidden in the slope of today. Let that thought ease you downward, like a line becoming a point. Now let's tilt the lens and see the world in pieces, each one adding up to something whole. You're standing at the edge of a river, watching drops of water flow by. Not one big splash, but countless tiny ripples weaving together. That's what integrals do. If derivatives are about change, integrals are about accumulation, adding up the little things to understand the big picture. Integral calculus asks, what happens when we gather everything, from start to finish? It's how we find the area under a curve, how we calculate distance from speed, how we understand growth, weight, volume, energy, even probability. It's the math of putting it all together. The most famous integral symbol, that long, elegant, is actually an old-fashioned S for sum, a gentle nod to the idea that we're summing up infinite little pieces, each one tiny but essential. There are definite integrals which give exact totals, like the area under a curve from point A to point B, and indefinite ones, which are more like general rules, formulas for what could be if we knew the limits. Here's your quirky tidbit. When Isaac Newton first described gravity, he used integrals to calculate the pull of the entire Earth on a falling apple. That's right. He figured out how to add up the influence of every particle of mass. And people say apples just fall. Scientists still argue about how to visualize integration. Is it really adding up slices? Is it the inverse of a derivative? Or is it a deeper metaphor of connecting fragments into a smooth, complete idea? So tonight, picture your thoughts like drops of water, collecting slowly in a bowl. One moment, another, then another, each one quiet, but together they build something, a sense, a shape, a feeling of fullness. You don't need to understand every drop, just know they count, every moment, every breath, gently summed into something whole. Now let's let the world wiggle a bit, because even the most chaotic signals have structure if you listen closely enough. You're watching ocean waves roll in. Some are gentle, some choppy. But somewhere beneath them all is a deeper rhythm, a hidden beat. That's the essence of the Fourier transform, a mathematical tool that takes messy signals and reveals their pure ingredients. Fourier analysis asks, what if every complicated wave is actually made of simpler waves? And then it answers, it is. Sound, light, vibrations, everything gets broken down into sine and cosine waves. It's like math whispering, don't worry, I can untangle this. You can take a jagged sound, even static noise, and break it into clean, smooth frequencies. It's how MP3s compress music, how MRI machines scan your brain, how astronomers study starlight. The Fourier transform doesn't just analyze, it hears the truth inside the noise. Here's your quirky tidbit. Jean-Baptiste Joseph Fourier, the French mathematician who pioneered this method, originally used it to study heat flow. People didn't believe him. Today, his work is used in everything from digital photography to earthquake detection. Not bad for a guy obsessed with baking equations. In mathematical terms, a Fourier transform takes a function from time-space and translates it into frequency space. It's like turning a symphony into a recipe. This much bass, that much treble, a sprinkle of hum. Scientists still argue over how to interpret Fourier transforms in certain contexts. Are we always hearing the real frequencies, or just rearranging the chaos into something useful? Either way, it's one of the most profound tools in applied math. So as you rest now, imagine the hum of your thoughts being gently decomposed into waves. Long, slow curves for memories, fast flickers for ideas. Every thought a note, every note part of a larger harmony. Because deep down, you're not noise, you're signal, softly singing in sine waves. Now let's tiptoe into the land of uncertainty, where math doesn't promise certainty, just possibility. You're holding a coin. You flip it. Heads, tails. You wait. But probability doesn't care about one coin. It's the math of many flips, of trends, of the soft patterns that emerge from randomness. It's the logic of uncertainty, whispered one outcome at a time. Probability isn't about fate. It's about expectation. It asks, what's likely? Not, what will happen? You don't need to predict every toss. Just understand the invisible bias leaning in the background. Even chaos, it turns out, has tendencies. You've met probabilities your whole life. Weather forecasts, insurance rates, sports stats. But underneath is a language of numbers. Outcomes, sample spaces, events. You assign a value between 0 and 1 to represent how likely something is. 0 means never. 1 means always. Everything else? Somewhere in the murky middle. Here's your quirky tidbit. The entire field of probability theory was partly born from a series of gambling letters exchanged between two 17th century French mathematicians, Pascal and Fermat, trying to figure out how to fairly split bets when a game is interrupted. You can thank card sharks for modern statistics. There are rules. The probability of all possible outcomes adds up to 1. The probability of two independent things both happening. Multiply their probabilities. Simple rules. Deep consequences. Flip enough coins and patterns emerge. Roll enough dice and the average becomes predictable. Scientists still argue about the philosophy behind it. Is probability about knowledge, what we don't know? Or is it a real force? Baked into the universe? Is randomness just ignorance in disguise? So tonight, imagine a million coins flipping in the darkness. You don't need to track them. Just feel the rhythm. Half land heads, half tails. Not every time, but eventually. Probability doesn't promise the next outcome. It whispers about the long run. Let that comfort you. Even in a world of randomness, math finds rhythm. And you, tonight, are drifting gently into the softest kind of uncertainty. Let's gently swirl into the fog where logic meets chance, where the world isn't binary, but probabilistic. You're standing at a fork in the road. One path leads to ice cream, the other to a mysterious door. You're told there's a 70% chance of sweetness and a 30% chance of surprise. You pause. Do you wait for more data or start calculating? This is where Bayesian probability lives, a softer, more curious way to measure uncertainty. Bayesian thinking flips the script. Instead of asking, what's the chance this happens? It asks, given what I know now, how should I update my beliefs? It's not about one-time odds. It's about learning as you go. The core idea: start with a guess, a prior, add new evidence, and adjust your thinking to get a posterior. You're always refining, always updating. It's probability as a conversation, not a verdict. Here's your quirky tidbit. Reverend Thomas Bayes never actually published his famous rule. It was discovered in his notes and published after his death. He was a minister doing math in secret, solving problems that would one day power everything from spam filters to self-driving cars. Bayes' rule is simple in form, but deep in power. It looks like a modest fraction, but that fraction fuels modern machine learning, medical diagnosis, risk modeling, and artificial intelligence. It helps systems make decisions under uncertainty, just like we do. Scientists still argue about how Bayesian methods stack up against classical or frequentist statistics. Do probabilities reflect truth, or just what we currently know? Some say Bayesianism is too subjective. Others say it's the only honest model for how real minds think. So tonight, imagine your thoughts updating gently, not abruptly, just soft revisions. A little more certain here, a little less there. Bayesian sleep mode. Every breath a new bit of evidence. Every exhale a quiet recalculation. You don't have to be sure of everything, just willing to adjust. Now let's walk into a maze, not with walls, but with logic, chance, and a whole lot of waiting. You're in a line at a bakery, only one clerk. People arrive randomly. The clerk serves them one at a time, sometimes fast, sometimes slow. Will you get your pastry before the cinnamon rolls run out? This is queuing theory, the math of waiting lines, and it's quietly running the world. Queuing theory studies how things move through systems when they can't all go at once. Customers in line, packets of internet data, airplanes waiting to land, calls on hold. It's the math of flow, and how to optimize it so the world doesn't grind to a halt. You might picture a line of people, but really you're modeling arrival rates, service times, capacity, and priority. You use probabilities, averages, and clever tricks to predict things like average wait time, queue length, or system overload. It's messy, but strangely elegant. Here's your quirky tidbit. During World War II, British engineers used queuing theory to improve radar signal processing and anti-aircraft gun coordination. Today, the same principles keep your food delivery app from imploding on a Friday night. Queuing theory touches everything. Hospitals use it to manage patient flow. Banks optimize teller availability. Even theme parks use it to design lines that feel fair and just long enough to build anticipation. Your phone deciding when to send that photo? Yep, there's a queue for that. Scientists still argue about human behavior in queues. We should be predictable, but we're not. People skip, balk, abandon. Sometimes we'd rather wait longer in a fast-moving line than stand still in a shorter one. Math models the system, but people always add a twist. So as you rest tonight, picture your worries lining up, one behind the other. No pushing, no rush. Each will be handled in time. The system is in place. The logic holds. You're not stuck. You're just in queue. And in this peaceful backlog, there's room for stillness. Now let's tumble into a realm where chaos makes patterns, and randomness becomes a painter. You're tossing a handful of dust into the air, and it lands in a perfect miniature galaxy. Strange, right? Welcome to the shimmering edge of mathematics. Fractals. Fractals are shapes that repeat at every scale. Zoom in, and you see the same pattern. Zoom in again. Still there. Forever. Coastlines, snowflakes, trees, lungs. Nature loves fractals. These are structures built on feedback, recursion, and infinite complexity packed into finite space. The most famous? The Mandelbrot set, a hypnotic swirl of shapes born from a simple equation and iterated endlessly. It looks like an alien jellyfish doing interpretive dance, but every bulge, every curl, holds infinite copies of itself. If math could dream, this is what it would see. Here's your quirky tidbit. In the 1980s, Benoit Mandelbrot showed that clouds, coastlines, and broccoli all obeyed fractal geometry. NASA even used fractals to compress satellite images. Suddenly, the universe didn't just look fractal, it was fractal. Fractals are everywhere. Lightning bolts, blood vessels, river networks. They help model chaos, systems too unpredictable for classic equations. Weather, stock markets, forest fires, not random, but sensitive. A small change, a massive ripple. Scientists still argue whether fractals reflect deeper truths or are just beautiful models. Can they truly explain complexity, or do they only mimic it? Some physicists think the universe itself may be fractal on the larger scales. Others shrug and keep zooming. So tonight, close your eyes and drift inward. Picture a fern leaf. Now zoom in on one leaflet, then another. Each one smaller, but just as detailed. It never ends. The deeper you go, the more there is. And strangely, the more it looks like the beginning. You're not lost in complexity. You're folded gently into it. Let's drift into the space between math and chance, where particles twitch, light flickers, and certainty evaporates. You're staring at a wall. A beam of light is shining through a slit. You expect a clean shadow. But instead, you get an interference pattern, dark and light stripes, like the universe can't make up its mind. Welcome to quantum probability, where classical math starts to unravel and reality gets weird. In the quantum world, things don't just are, they might be. A particle doesn't have a definite position until it's measured. Until then, it exists in a cloud of probabilities. Not this, not that, but both. And the math used to describe this. It's still math, but wrapped in uncertainty and woven with complex numbers. Instead of flipping a coin and getting heads or tails, quantum mechanics flips both until you peak. That's the superposition principle. And probability here isn't just about outcomes. It's about amplitudes, numbers that, when squared, give the chance of finding something in a certain state. Here's your quirky tidbit. In 1935, Schrödinger proposed his famous cat thought experiment, a feline sealed in a box, both alive and dead until observed, to show how absurd quantum superposition seems when scaled up. That poor imaginary cat has become the symbol of quantum confusion ever since. Quantum probability helps predict the behavior of subatomic particles, the orbits of electrons, and even tunneling effects where particles slip through barriers like ghosts. It's math operating on the edge of knowability, and it underpins the physics of everything from lasers to MRI scanners. Scientists still argue about what quantum probability means. Is it just a tool, or does it reflect a fundamental randomness in nature? Some physicists cling to determinism, others embrace the fuzz. The math works either way. It just doesn't always comfort. So as you sink into stillness, imagine yourself as a wave function, spread out, relaxed, undefined, not fixed, not decided, just floating in possibility, waiting for the universe to whisper a decision. Tonight, you don't need to collapse into certainty. You're allowed to remain both. Now let's step into the realm of decisions, not made by dice, but by math that weighs every move. You're playing a game, not just for fun, but with stakes. You have choices. So does your opponent. You try to guess what they'll do, while they're guessing what you'll do. Welcome to game theory, the elegant science of strategy, bluffing, and the occasional betrayal. Game theory isn't about video games or Monopoly. It's about situations where multiple players, each with different goals, interact. It asks, what should I do, knowing that they're also thinking? It's the math of decision-making under competition. At the heart is the Nash equilibrium, named after John Nash, whose story you might remember from A Beautiful Mind. It's a state where no player can improve their position by changing strategy, as long as everyone else stays put. It's not necessarily the best outcome, just the most stable. Here's your quirky tidbit. During the Cold War, game theory helped guide nuclear strategy. The logic of mutually assured destruction is pure game theory. Each side deterred from striking first, because doing so would guarantee its own end. Comforting, right? Game theory applies to economics, politics, biology, and dating apps. When companies set prices, when nations negotiate treaties, when animals compete for territory, game theory is lurking beneath, quietly calculating. You've probably used it without realizing. Choosing the fastest grocery line, strategizing during a board game, deciding whether to swerve in Mario Kart. If you've ever second-guessed someone else's guesswork, you've done game theory. Scientists still argue over how rational real humans are. Game theory often assumes perfect logic, but we're full of emotion, misjudgment, and weird choices. Behavioral game theory is a growing field, blending math with psychology. So tonight, picture yourself in a quiet game. No noise, no pressure. You make your move. They make theirs. Not to win, not to lose, just to dance. Strategy becomes rhythm. Reaction becomes flow. And in this infinite loop of choice and chance, you're not outwitted, you're in balance. Now let's step onto the grandest stage of math, where patterns echo across centuries and mysteries still whisper behind prime walls. You're walking a long hallway, and along the floor are tiles, some plain, some glowing. The glowing ones, those are prime numbers. Numbers only divisible by 1 and themselves. 2, 3, 5, 7, 11. You step lightly, but they're scattered with no obvious rhythm. Or are they? Welcome to the Riemann hypothesis, one of the deepest unsolved problems in all of mathematics. It's a statement about the distribution of prime numbers, and it lives in the surreal world of complex analysis, where the real and imaginary blend. It all revolves around the Riemann zeta function, a strange, twisty function that takes complex numbers as input and produces complex output. When you graph it, it looks like a river of spikes and zeros. And those zeros, that's where the magic lives. The hypothesis says, all non-trivial zeros of the zeta function lie on a straight line. If true, it would explain why primes seem random, but aren't. It would connect chaos with structure, noise with music. Here's your quirky tidbit. This problem is so tough and so important, it's one of the 7 Millennium Prize problems. Solving it earns you $1 million and eternal bragging rights. So far, no one's cracked it, but many have tried, carefully, quietly, sometimes obsessively. Riemann's original paper on the subject was just 9 pages long, but it launched entire fields of study. The hypothesis is the heartbeat behind much of number theory and encryption. Primes guard secrets, and this problem holds the master key. Scientists still argue whether the hypothesis will be proved in our lifetime. Some think it's just a matter of time. Others suspect we need new math entirely, and a few whisper that it might not be true at all. So tonight, picture a long string of numbers twinkling like stars. Some shine brighter, some stand alone, but beneath them all, a hidden rhythm pulses, just out of reach. You don't have to solve it. Just feel the harmony beneath the chaos. And maybe, in dreams, the line becomes clear. Now let's tiptoe into the strange whispering corners of mathematics, where the infinite doesn't just stretch, it stacks. You're sitting at a table with a pile of cards. You take half, then half of what's left, and again, and again. The pile never disappears. It just gets thinner and thinner. You've stumbled into the realm of infinity, not as an idea, but as something you can work with. Infinity isn't just a really big number. It's its own world. There are different sizes of infinity. Some infinities are bigger than others. That's not poetic. It's mathematical fact. Welcome to set theory and the quietly mind-bending ideas of Georg Cantor. Cantor discovered that the set of all whole numbers is infinite, but you can still list them. 1, 2, 3, and so on. That's called countable infinity. But the set of real numbers, everything between 0 and 1, including all the decimals you can't write down, that's uncountable. Bigger, incomparably so. Here's your quirky tidbit. Cantor's work on infinity was so radical that it made some of his peers furious. One called it a grave disease. Even Cantor himself struggled with depression, haunted by the implications of his work. But today, he's remembered as the father of the infinite. Mathematicians use the symbol, aleph, to represent different sizes of infinity. 0 is the smallest infinity, like the natural numbers, but beyond it lies aleph 1, aleph 2, and so on. A towering, endless staircase of infinitudes. Scientists still argue about the continuum hypothesis, the idea that there's no set size between the countable numbers and the real numbers. Is 1 the size of the continuum? No one knows. Even more mysterious, it turns out this hypothesis can't be proven true or false using current mathematics. It floats, unresolved, like a ghost in the attic of set theory. So as you rest now, imagine yourself stepping down a staircase that never ends. Each step smaller than the last, yet always leading somewhere. You're not falling, you're exploring. Infinity isn't a destination. It's the architecture of thought. And in its quiet hallways, math keeps unfolding. Now let's climb higher, past equations and coordinates, into the realm where math becomes shape, but not the kind you can draw. You're walking across a surface. It feels smooth at first, like the skin of a balloon. But as you keep walking, the rules start to shift. Angles warp, distances deceive. You've stepped into topology, the math of shape, without the fuss of geometry. Topology isn't about size or angles. It's about structure, a coffee cup and a donut. In topology, they're the same, because both have one whole. As long as you don't tear or glue anything, the shapes are equivalent. Stretch it, bend it, twist it. Topology doesn't mind. This discipline studies how spaces are connected. What stays the same when you warp a shape continuously? That's a topological invariant, like the number of holes, or whether something's in one piece. Here's your quirky tidbit. The most famous topological object might be the Mobius strip, a surface with only one side. Take a strip of paper, give it a twist, and tape it together. Now try drawing a line on it without lifting your pen. You'll go around both sides, without ever flipping over. It's strange, and kind of magical. Topology helps us understand the shape of the universe, the form of DNA strands, and even how spaces behave in higher dimensions. It's used in data science, neuroscience, and robotics. Anywhere structure matters more than measurements. Scientists still argue over how to visualize high-dimensional topological spaces. Our brains evolved in 3 dimensions, but topology doesn't care about our limitations. It stretches and folds space into forms that feel like puzzles from another reality. So tonight, imagine drifting along the edge of a shape that never ends, softly twisting, gently curving, never tearing. You're not navigating points. You're feeling the space between them. Not measuring, but understanding. And maybe, just maybe, that Mobius strip under your pillow is a doorway to somewhere weirder. Now let's unravel the math of motion. Not just things moving, but how they dance with time. You're watching a pendulum swing. Back and forth, gently. Predictable, right? But now, imagine the pendulum starts shifting. Faster, slower, pulling toward a new direction. You've entered the world of differential equations, where change writes the rules, and every motion is a solution waiting to be traced. Differential equations describe how things evolve, not just where they are, but how they're moving. They connect rates of change to the state of a system. A car speeding up, a population growing, a planet orbiting, all follow differential equations like quiet scripts. There are ordinary differential equations, which deal with one variable, like time. And there are partial differential equations, which track changes across multiple dimensions, used in fluid dynamics, heat transfer, sound waves, even the way galaxies swirl. Here's your quirky tidbit. The famous Navier-Stokes equations, which describe the motion of fluids, remain so tricky that solving them in all cases is another one of the Millennium Prize problems. $1 million still waits for anyone who can tame the math behind a splashing glass of water. Differential equations don't always have neat solutions. Sometimes they spiral into chaos, requiring approximation, simulation, or a really patient supercomputer. But when they do resolve, it feels like watching the gears of reality click into place. Scientists still argue whether all systems can truly be modeled with equations like these, or whether life itself occasionally escapes math's grasp. Some systems behave too wildly. Others appear orderly, but mask hidden turbulence beneath the surface. So tonight, imagine your thoughts as curves, each one governed by quiet rules of change. Not static snapshots, but soft trajectories. You're not locked in place. You're evolving, following your own elegant differential path, bending slowly toward calm. And the equation of you, still unwritten, still solving itself. Now let's drift into the realm of shapes that move, where space itself can stretch, squish, and spin. You're watching a flexible sheet of rubber. You draw a square on it, then pull the edges. The square becomes a rhombus, then a blob, then something unrecognizable. This is the world of linear transformations, and it's all powered by matrices. You've met matrices before, a tidy grid of numbers. But now, they're not just static tools. They're functions. Each matrix becomes a machine. You feed in a vector, and it spits out a transformed version. It rotates it, stretches it, projects it onto a shadowy plane. Linear transformations are how we describe geometric change. Want to rotate an object? Matrix. Want to scale, reflect, or shear it? Matrix. They're like the language of spatial logic, whispered in rows and columns. Here's your quirky tidbit. In video games, when you see a character move, jump, or turn, linear transformations are doing the behind-the-scenes work. Every explosion, every shifting camera angle, every spinning coin, it's math under the hood, keeping the illusion smooth. The beauty lies in eigenvectors and eigenvalues, those magical vectors that don't change direction when transformed. They just stretch or shrink. It's like finding the calm in the middle of a storm, a direction that stays true even as everything else moves. Scientists still argue over the best way to teach these concepts. Should we start with intuition, geometric transformations, or dive into the abstract, letting the algebra guide the understanding. Either way, the applications are everywhere. Physics, 3D modeling, machine learning, economics. So tonight, picture your thoughts as arrows, vectors in space. A quiet matrix hovers nearby, nudging them gently. Some rotate, some grow, some settle into place. Each transformation smooth, silent, inevitable. You don't have to force your thoughts into stillness. Just let the matrix do its work. Quiet transformations while you rest. Now let's dive into a space where randomness becomes geometry and patterns bloom from chance. You're standing in a meadow, tossing seeds into the wind. They land here, there, everywhere. Over time, a patchy pattern appears. Not uniform, not ordered, but not chaotic either. This is the world of stochastic processes, where randomness evolves, step by unpredictable step. Stochastic processes are sequences of random events that unfold over time. Think of a drunk person stumbling through a park, each step uncertain, but still moving forward. That's a random walk, and it's a classic stochastic model. It sounds silly, but it's used to model particles, stock prices, and even genetic drift. These processes are everywhere. The flutter of stock market graphs, the flicker of radioactive decay, the shuffling of cards, even how rumors spread or diseases move through populations, all follow the rules of stochastic behavior, where the next move depends partly on chance. Here's your quirky tidbit. The field exploded thanks to Norbert Wiener, who helped develop the mathematical model behind Brownian motion, the jittery movement of particles in liquid. It's sometimes called a Wiener process, which may be the only time math sounds like a hot dog stand. One particularly dreamy example? Markov chains. In these systems, the next state depends only on the current one, not the whole past. Memoryless math. You're not haunted by what happened before, only what's happening now. Scientists still argue whether randomness is fundamental or just a veil over deeper deterministic rules. In either case, stochastic processes give us a way to work with uncertainty, not fear it. So tonight, imagine your thoughts as leaves drifting in the wind, not stuck, not lost, just dancing to probabilities. You're following a path, even if you don't know where it leads. And that path, while unpredictable, still has a pattern, still has grace. Sleep, after all, is a kind of random walk too. And tonight, you're headed somewhere gentle. Now let's press our ear to the heartbeat of networks, where everything connects and every connection counts. You're looking at a web, not a spider's, but one made of dots and lines. Some dots are busy, with lines going everywhere. Others sit quietly on the edge. This is graph theory, the study of connections, paths, and the strange beauty of linked systems. Each dot is a node, or vertex, and each line is an edge. That's it, so simple. But from that simplicity grows complexity. Friend groups on social media, airline routes, neural networks, molecules, the internet itself, all of it, graphs. Graph theory asks questions like, is there a path that visits every node exactly once? That's the Hamiltonian path. Or, what's the shortest route through all your errands? That's the traveling salesman problem, still unsolved in general. Or even, can you color a map with just 4 colors without adjacent regions matching? That took over a century to prove and required a computer to finally settle. Here's your quirky tidbit. The entire field of graph theory began with a casual 18th century math stroll. Euler, curious about the layout of bridges in Königsberg, asked whether one could cross each bridge exactly once. His answer? No. And in solving it, he unknowingly invented a whole branch of math. Today, graphs help manage traffic, model epidemics, build recommendation systems, and map relationships between genes. Every time your GPS reroutes you, thank a graph. Every time a website suggests a new video, graph again. Scientists still argue about graph isomorphism, how to efficiently tell if two graphs are really the same, just rearranged. It's simple to state, but no one's found a perfect solution that always runs quickly. Another math whisper left unsolved. So tonight, picture your thoughts as glowing dots, softly connected by threads. Ideas linking to memories, memories to dreams, a vast network of you lit up like a constellation. You're not alone out there. You're a node in something beautiful, connected, and gently humming. Now let's slide quietly into the world of choices and fairness, where math steps in to help you divide, decide, and negotiate without flipping a coin. You're at a table with a cake. It's your birthday, but you're not alone. You and your friends want slices, equal ones, or at least fair. But what does fair even mean? This is where combinatorics and fair division step in, quietly balancing the slices of life. Combinatorics is the math of counting, not just how many, but how many ways. It asks, how many different paths? How many different groups? How many different cake slicing strategies that keep everyone happy? Say you have 5 toppings and you want to choose 3. How many combinations are there? What if you care about order? That's permutations. What if the toppings can repeat? The rules shift again. It's like math playing with Lego bricks, rearranging, snapping, building countless possibilities from a small set of pieces. But then we dive deeper into problems of allocation and decision-making. How do you fairly divide limited resources? One famous idea is the I cut, you choose method. Simple, but powerful. Another is the envy-free division, where no one feels shortchanged. Trickier than it sounds, especially when people value things differently. Here's your quirky tidbit. Mathematicians once used combinatorics to settle an actual cake-dividing dispute involving roommates, frosting placement, and who got the corner piece. The solution involved geometry, negotiation, and surprisingly, no food fights. Scientists still argue over the best definitions of fairness. Is it equality, equity, satisfaction? In mathematics, fairness can be quantified, but in life, it's often emotional. That's where math tries to offer calm, structured choices amid human fuzziness. So tonight, imagine your thoughts like toppings on a cake. Some ideas you want more of, some you'd gladly share. And with each decision, combinatorics offers a whisper. There's always another way to divide. You don't need to solve it all. Just know that there's math quietly watching over the split, and it's rooting for everyone to get a fair piece. Now let's walk into a world built not from shapes, but from logic itself, where statements turn into structures and truth becomes geometry. You're standing in a room full of sentences. Some are true, some false. Some depend on others like dominoes. But instead of grammar, you're arranging axioms, propositions, and proofs. This is mathematical logic, where thought is the raw material, and reasoning is the architecture. Mathematical logic studies the foundations of math. What can be proven? What can't? It's not about solving equations. It's about asking, why does this work in the first place? Logic lays the tracks. All the other trains, algebra, geometry, calculus, they ride on rails built by logic. At its core is the concept of formal systems, self-contained worlds made from a few basic rules. From there, you build, slowly, carefully, like Lego bricks made of truth. But then come the limits, like Gödel's incompleteness theorems. Here's your quirky tidbit. In the 1930s, Kurt Gödel proved something mind-blowing. In any consistent mathematical system complex enough to include arithmetic, there will always be true statements that can't be proven. That's right. Math has mysteries baked in, like a puzzle with one piece missing on purpose. Mathematical logic powers everything from computer science to linguistics to the way we build secure systems. It's the reason software runs reliably. It's how AI makes decisions. It's the circuitry of thought, distilled into symbols. Scientists still argue about the implications of these foundational limits. Does it mean math is incomplete, or just beautifully endless? Are we exploring something real, or just building cathedrals in our minds? So tonight, imagine your thoughts like a proof. One idea leads to another, a quiet chain of implication, not always complete, not always provable, but coherent, structured, satisfying. You don't need all the answers. Some truths live just beyond the page, and that's okay. The logic still holds, and you're wrapped inside it. Now, let's venture into the curved corners of space, where geometry doesn't follow the rules you grew up with. You're tracing the edge of a triangle, but something feels off. The angles don't add up to 180 degrees. In fact, they add to more, or less. Welcome to non-Euclidean geometry, where space bends and the familiar becomes flexible. Euclidean geometry, the one you learned in school, assumes flatness. Parallel lines never meet. Triangles behave. Circles are well-behaved citizens. But change just one postulate and a whole new universe unfolds. There are two main flavors of this strange geometry. Hyperbolic geometry, where space is negatively curved, like a saddle. And elliptic geometry, where space curves positively, like the surface of a sphere. In these worlds, parallel lines can diverge, or even intersect. Up can loop back around to down. Here's your quirky tidbit. In hyperbolic space, you can fit infinitely many triangles inside a finite area. It's like a magical pocket universe where geometry folds inward, creating room where none should exist. Mathematicians even knit physical models of it, curvy, roughly creations called hyperbolic crochet. Non-Euclidean geometry isn't just a curiosity. It forms the backbone of general relativity, Einstein's theory of gravity. Space and time are curved by mass, and objects follow paths, geodesics, through this flexible fabric. Without non-Euclidean geometry, we'd never understand black holes, GPS, or how light bends around stars. Scientists still argue how best to visualize these bizarre spaces. Our brains are wired for flat thinking, but models, projections, and even virtual reality help us glimpse their surreal contours. So tonight, picture yourself walking on a softly curved surface. You keep going straight, but somehow end up where you started. Angles stretch and contract like breath. Space itself exhales around you. You don't have to unlearn everything. Just know that reality isn't flat. And your thoughts, they curve too, gently, beautifully, bending into the unknown. Now let's unfold into dimensions your senses can't touch, where space isn't just wide or deep, but far more layered than you ever imagined. You're standing in a room. You move forward. 1 dimension. Slide left. 2. Duck down. 3. That's your world. 3 familiar axes, comfortably navigated. But what if there's more? What if reality has extra dimensions, invisible, but just as real? Mathematicians have no trouble imagining 4, 5, or 100 dimensions. We can't see them, but we can describe them. Welcome to higher dimensional geometry, where shapes grow strange and distance behaves like a dream. A 4-dimensional cube. It exists, mathematically. It's called a tesseract, not science fiction, just math. Its shadow looks like a cube inside another cube, connected by ghostly lines. And just like we unfold a 3D box into 6 squares, you can unfold a tesseract into 8 cubes. Here's your quirky tidbit. String theorists believe the universe may actually have 10 or even 11 dimensions, most of them curled up so tightly we'll never detect them. Like secret hallways behind the drywall of space, higher dimensions show up in practical places too. In machine learning, data isn't just plotted on an XY graph. Each feature, height, weight, preference, pixel color, adds another dimension. Algorithms navigate these high-dimensional feature spaces to sort, recognize, and predict. Scientists still argue whether these extra dimensions are physically real or just useful mathematical fictions. Some say they're metaphors for complex relationships. Others believe they're as real as the 3 you use every day, just hidden, curled, inaccessible. So tonight, close your eyes and imagine walking in a space you can't see. You step in a direction that doesn't exist in your waking world. It doesn't feel like up or forward, but it's there, and it's spacious. Your thoughts tonight aren't limited to 3 dimensions. They stretch, twist, and bloom into places without names. You're not boxed in. You're just folded, waiting to unfold. Now let's float into the realm where symmetry becomes sacred, and structure hums with hidden order. You're staring at a snowflake. Perfect, balanced. Every branch mirrors its siblings. Now zoom out. Crystals, galaxies, even music. Symmetry echoes through nature. But math doesn't just admire symmetry. It studies it, builds with it, and names it. Welcome to group theory, the quiet language of balance. In group theory, a group is a collection of things that can be combined in a way that follows 4 simple rules: closure, associativity, an identity element, and an inverse for every member. It sounds dry, but these things can be numbers, movements, even cube twists. And the rules, they define how systems behave when they try to keep their structure, rotating a square. Those movements form a group. Twisting a Rubik's Cube, that's group theory doing gymnastics, flipping, spinning, sliding. So long as it returns to where it started, you're in group territory. Here's your quirky tidbit. Mathematicians once discovered a group so large and intricate, they called it the monster group. It has over 8 by 153 elements, more than the number of atoms in the Earth, and its unexpected connections to string theory and modular functions are still baffling researchers. It's sometimes called the friendly giant of symmetry. Group theory doesn't just apply to puzzles, it governs the laws of physics. Particle physics uses group theory to classify subatomic particles. Quantum mechanics, crystallography, even music theory, they all bow to the idea of symmetry and structure. Scientists still argue about how to visualize complex groups. Some can be drawn. Others live in abstract algebraic space, more felt than seen. but they all whisper the same thing. If something moves and comes back, there's a pattern. So tonight, picture your dreams as mirrored halls. You turn, and the world reflects itself. You move, and the pattern remains. There's comfort in knowing that motion doesn't destroy beauty. It reveals it. Sleep now, inside the geometry of balance. Let symmetry hold you steady. Now let's wade into the ocean where data hides. Waves of numbers, ripples of meaning, and signals waiting to be understood. You're handed a list of numbers, just digits, cold and quiet. But somewhere inside is a heartbeat, a trend, a story. This is statistical inference, the art and science of drawing conclusions from data without jumping to the wrong ones. Statistics isn't just about counting or averaging. It's about estimating the unknown from the known. You don't survey every person on Earth to guess who's going to win an election. You sample a few, and if you're careful, your math does the rest. At the heart of it, the idea of a population and a sample. You observe part of a system, then use probability to infer things about the whole. It's like trying to guess the flavor of a cake by tasting a single crumb. Not perfect, but better than licking the pan. Here's your quirky tidbit. One of the first uses of modern inference came from Guinness. Yes, the beer company. They hired a statistician, William Gossett, who developed what's now called the student's t-test to test the quality of their batches. And no, he wasn't allowed to publish under his real name, so he picked student. There are two pillars here: estimation and hypothesis testing. Estimation asks, what do we think the true value is? Testing asks, are we seeing something real or just noise? Confidence intervals, p-values, significance levels. It's like math wearing a lab coat. Scientists still argue about the meaning of statistical significance. Does a p-value really prove anything? Or just suggest we look closer? As our data gets bigger and noisier, the tools get more powerful, but also more fragile. So tonight, imagine drifting on a sea of numbers. You're not trying to memorize them. Just feel their pull. Some waves rise, some fall. But a pattern glimmers beneath. You don't need to know everything with certainty. Just trust the signal beneath the noise. Now let's step into the vault where secrecy and numbers intertwine, where messages hide in plain sight, locked with keys only math can forge. You're writing a note, a secret one. You don't want anyone to read it, except one person far away. You whisper your message and wrap it in numbers. This is cryptography, the ancient, and now digital art of keeping secrets through math. Cryptography today is all about algorithms and impossibilities. It's not about hiding a message. It's about making it unreadable without the key. Even if someone intercepts it, they can't understand it. It's scrambled, shielded by layers of prime numbers, modular arithmetic, and clever tricks from number theory. One of the core tools, public key cryptography. You publish one key for the world to use and keep another private. Anyone can lock a message for you, but only you can unlock it. It's like a mailbox with a transparent slot, open to receive, but locked shut from the outside. Here's your quirky tidbit. The RSA algorithm, still used today, relies on the fact that multiplying two giant prime numbers is easy, but factoring the result is insanely hard. No known shortcut. Even with modern supercomputers, cracking a well-built RSA key would take billions of years, probably longer than the Earth has left on its lease. Cryptography powers your life more than you realize. Every time you buy something online, send a private message, or sign into an account, math is wrapping your information in armored encryption, quietly, invisibly. Scientists still argue about the future of cryptography in a post-quantum world. Quantum computers could break today's encryption schemes in hours or minutes. So new protocols are being tested, hardened, prepared. So tonight, imagine your thoughts like glowing orbs. You gently seal each one in a mathematical lockbox. No one else can peek, not even the future. You carry your secrets with elegance, numbers holding them tight. And in the silence of sleep, math keeps watch, like a key turning in a lock just once perfectly. Now let's walk into a labyrinth, where decisions branch like trees, where each step narrows your future, and math lights the path. You're playing a game. Each choice you make opens a new door. Behind every door, more choices. Some lead to treasure, some to traps. You need a guide, not just a gut feeling, but a map of logic. This is decision theory, the quiet navigator of risk, reward, and reason. Decision theory blends probability, utility, and logic into a system for making choices. It asks, what's the best thing to do, given what I know? You list your options, weigh the outcomes, add probabilities, then run the math. It's like putting your intuition through a calculator. A key tool, the decision tree. Each branch is a possible choice, each leaf an outcome. You walk the tree, calculating expected values, combining how likely something is with how good or bad it would be if it happened. It's math trying to be wise. Here's your quirky tidbit. Decision theory has guided everything from poker strategies to nuclear deterrence plans. There's even a branch called Minimax, designed to minimize your maximum regret. A way to make choices not just based on winning, but on avoiding the worst kind of I told you so. Decision theory is used in AI, economics, medical diagnosis, even dating apps. Any situation where choices must be made with limited info and consequences hang in the balance. It doesn't promise certainty, it offers clarity. Scientists still argue whether humans actually follow rational decision models. We're supposed to, but our brains often favor shortcuts, emotion, and gut feelings. That's why behavioral economics is full of surprises. Math knows the correct answer. We often don't choose it. So tonight, picture your thoughts branching softly. Each idea a pathway. Some fade, others flower. You don't need to find the perfect route, just one that leads to peace. Math can't guarantee outcomes, but it can help you walk forward gently even when the future is foggy. Now let's step into a realm where randomness becomes rigor, and risk is no longer reckless. It's measured, priced, and quietly managed. You're holding a deck of cards and a small pile of chips. You bet, you win, you lose. But behind the thrill, there's something deeper. Mathematical finance, where markets are modeled, derivatives dissected, and uncertainty is woven into value. Finance isn't just about money. It's about predicting and managing change. Mathematicians don't see dollars. They see stochastic processes, interest rate curves, risk functions. They build models that try to answer questions like, what's this asset worth if the future is unknown? Or, how can I hedge against disaster? At the heart of it, the Black-Scholes equation, a partial differential equation used to price options. It treats the value of financial contracts like particles drifting in a fog of uncertainty. Smooth, continuous, and shockingly elegant for something that predicts what your stock might do. Here's your quirky tidbit. The Black-Scholes formula helped kickstart the explosion of derivatives markets in the 1980s. One of its inventors, Myron Scholes, won a Nobel Prize. Another, Fisher Black, sadly passed before the honor. But their work remains one of the most used tools in Wall Street's toolbox. Mathematical finance uses tools from probability, calculus, linear algebra, and even chaos theory. Traders might not realize it, but every financial model rests on decades of mathematical scaffolding. Scientists still argue about the reliability of these models, especially after major market crashes. Can math really predict human behavior under stress? Can a curve account for panic? Some say yes, with enough data. Others say no, because emotion defies equations. So tonight, imagine your worries like volatile stocks. They rise, they fall. But in the long run, the curve smooths. Math watches the drift, not the noise. You don't have to beat the market of your mind. Just hedge your thoughts. Diversify your dreams, and let the numbers work while you sleep. Now let's slip into the realm where machines learn, not by memorizing, but by recognizing, adapting, and quietly improving with every pattern they see. You're feeding a machine examples, pictures, sounds, numbers. And with each one, it gets a little smarter. Not because you told it what to do, but because math helped it find the structure. Welcome to machine learning, where algorithms discover truths hidden in data. Machine learning is built on a foundation of linear algebra, probability, optimization, and statistics. The goal? Create models that can generalize. That means not just learning from data, but making smart guesses on new data. Cats today, new cats tomorrow. One of the core ideas is training. You give the machine input-output pairs, and it adjusts its internal parameters, often weights in a matrix, to reduce the error. This is called gradient descent, a process of slowly stepping downhill, like a hiker in thick fog, trying to find the lowest valley of mistakes. Here's your quirky tidbit. The phrase neural network was inspired by real brains, but today's versions are more like math factories than mind replicas. They don't think, they just map complex inputs to outputs. And sometimes they do it better than us. From spam filters to voice assistants to self-driving cars. Machine learning is in your pocket, your inbox, your playlists. It recommends what to watch. It finishes your sentences. It even helps doctors detect diseases earlier than ever before. Scientists still argue about explainability. These models can be incredibly accurate, but often behave like black boxes. Why did it make that decision? What's going on inside? We know the math, but the emergent behavior sometimes feels uncanny. So tonight, picture your thoughts as data points, your dreams as training sets. Each night of sleep, another iteration, another gentle adjustment. You're not perfect, but you're improving. And just like those models, you don't need to know why everything works, just that you're learning, softly, all the time. Now let's slip into the realm where machines learn, not by memorizing, but by recognizing, adapting, and quietly improving with every pattern they see. You're feeding a machine examples, pictures, sounds, numbers. And with each one, it gets a little smarter. Not because you told it what to do, but because math helped it find the structure. Welcome to machine learning, where algorithms discover truths hidden in data. Machine learning is built on a foundation of linear algebra, probability, optimization, and statistics. The goal? Create models that can generalize. That means not just learning from data, but making smart guesses on new data. cats today, new cats tomorrow. One of the core ideas is training. You give the machine input-output pairs, and it adjusts its internal parameters, often weights in a matrix, to reduce the error. This is called gradient descent, a process of slowly stepping downhill, like a hiker in thick fog, trying to find the lowest valley of mistakes. Here's your quirky tidbit. The phrase neural network was inspired by real brains, but today's versions are more like math factories than mind replicas. They don't think, they just map complex inputs to outputs. And sometimes they do it better than us. From spam filters to voice assistants to self-driving cars. Machine learning is in your pocket, your inbox, your playlists. It recommends what to watch. It finishes your sentences. It even helps doctors detect diseases earlier than ever before. Scientists still argue about explainability. These models can be incredibly accurate, but often behave like black boxes. Why did it make that decision? What's going on inside? We know the math, but the emergent behavior sometimes feels uncanny. So tonight, picture your thoughts as data points, your dreams as training sets. Each night of sleep, another iteration, another gentle adjustment. You're not perfect, but you're improving. And just like those models, you don't need to know why everything works, just that you're learning, softly, all the time. Now let's descend into the quiet world of hidden structures, where signals become smooth melodies and chaos becomes clarity through transformation. You're listening to a song. It's a jumble of beats, bass, melody. But what if you could see every frequency at once, stretch out time and sound across a grid? This is the world of the Fourier transform, the math that turns signals into symphonies. At its core, the Fourier transform takes a function, often a wave, and expresses it as a sum of sine and cosine waves. That's it. Every sound, every image, every vibration can be broken down into simpler periodic components. Like math finding the pure notes beneath the noise. It's how we compress music, sharpen MRI images, and detect gravitational waves. Every time your phone recognizes a voice or your GPS filters signal noise, it's doing Fourier transforms behind the scenes, spinning complexity into clarity. Here's your quirky tidbit. Joseph Fourier, the 19th century French mathematician who pioneered this idea, was originally studying heat. He found that heat flow through a metal rod could be modeled using an infinite series of sine waves. Heat and harmony, unlikely partners. Fourier analysis doesn't just simplify, it reveals. In digital communication, it turns scattered data into clean channels. In quantum physics, it converts between position and momentum. Even the sound of your favorite lo-fi playlist passes through a quiet Fourier filter before it reaches your headphones. Scientists still argue about the best way to apply this technique to short-lived or non-repeating signals. That's where wavelets and short-time Fourier transforms come in, refinements for a not always perfect world. But the core idea still stands. Every signal has a deeper song. So tonight, imagine your thoughts as signals. Some soft, some jagged. Each one passing through a mental filter, decomposed, smoothed, understood. You don't have to silence the noise. Just recognize its frequencies. Let them separate, stretch, and settle. The chaos becomes music. The math becomes rest. Now let's stroll through spaces that measure distance, not with rulers, but with meaning, where nearness isn't physical, but mathematical. You're walking between two ideas, Not places, not numbers, just abstract things. How far apart are they? That's the magic of a metric space, a framework where distance applies to anything you can compare. Welcome to the geometry of generality. A metric space is a set with a rule for measuring distance between its elements. That's it. The rule, called a metric, must obey a few polite principles. The distance is always positive unless you're at the same point. Symmetric, the path there is the same as the path back, and it respects the triangle inequality. The long way around is never shorter. In Euclidean space, the metric is just the distance formula. But in other spaces, you can define distance based on time, energy, difference in color, even how different two pieces of text are. It's all about context. Here's your quirky tidbit. In the world of internet search engines, metric spaces help rank web pages. One common metric, edit distance. How many changes it takes to turn one word into another. Google might not care how far you are from pizza, but it cares how close your typo is to pepperoni. Metric spaces also show up in functional analysis, where functions themselves become points. You can measure how close two curves are. In data science, clustering algorithms use metrics to group similar data points, turning foggy blobs into meaningful patterns. Scientists still argue about the best choice of metric for different problems. Sometimes the natural one leads to messy results, while a stranger one reveals elegant structure. Math, like life, depends on how you choose to measure it. So tonight, imagine your thoughts floating in space, not defined by coordinates, but by how they relate. Some are close, some are far. Some drift apart, others cluster softly. You don't need a ruler to find peace, just a sense of what truly brings you nearer to calm. Now let's peek behind the curtain of math's decision makers, where some problems are solvable and others politely decline. You're staring at a puzzle. You try this, you try that. Hours pass. Then a strange question creeps in. Not how to solve it, but whether it can be solved at all. Welcome to computability theory, where we ask what problems math and machines are even allowed to answer. Computability theory is the study of what can be computed in principle. Not whether it's easy, just whether it's possible. It was born in the 1930s, when brilliant minds like Alan Turing began asking, what can a machine do, given infinite time and paper? Turing imagined a simple machine, a strip of tape, a read-write head, a set of instructions. This Turing machine could simulate any computation, no matter how complex. But he also showed there are problems even these perfect machines can't solve, like the famous halting problem. Can a machine tell if another machine will run forever? Nope. Here's your quirky tidbit. Turing's work wasn't just theoretical. It laid the groundwork for modern computers. And during World War II, he helped crack Nazi codes with early computing machines, arguably shortening the war by years. Secret math, saving lives. Computability theory draws the boundaries of the possible. It separates problems into decidable, solvable by some algorithm, and undecidable, forever outside our reach. And it reveals something quietly humbling. Even in math, some doors stay locked. Scientists still argue about Church-Turing thesis, the idea that anything we could possibly compute, we can simulate with a Turing machine. It's not a proof, it's a belief. A guiding star at the edge of logic. So tonight, let go of the pressure to answer every question. Some things aren't broken. They're just unsolvable, and that's okay. In your mind's quiet machine, let the unsolvable drift gently by. You don't need to halt them. Just observe, accept, rest. Now, let's drift into the vast digital landscape where math quietly decides how fast things move and whether they can ever be efficient at all. You're standing in a room full of locked doors. Each door has a puzzle. Some open instantly. Others take hours. Some might never open, no matter how long you try. This is the world of computational complexity, where we ask not just if something can be solved, but how hard it is to do so. Computational complexity classifies problems based on the resources, like time and memory, needed to solve them. Some problems are easy, meaning they can be solved in polynomial time. These live in a class called P. Others are verifiable in polynomial time, even if solving them takes forever. These live in NP. The golden question: is P equal to NP? In other words, if you can check a solution quickly, can you also find it quickly? It sounds simple, but solving it would shake the foundations of math, cryptography, and computing. It's another Millennium Prize problem, still unsolved. Here's your quirky tidbit. Some puzzles, like Sudoku, are NP complete. That means if you find a fast way to solve them, you've basically cracked the entire class. So yes, if your brain solves every Sudoku instantly, you're sitting on a Nobel-level revelation. Also, please call a mathematician. Computational complexity also deals with problems that explode in difficulty as they grow. These are intractable, doable for small inputs, but laughably impossible for large ones. Like finding the best route through 100 cities. There are more possibilities than atoms in the universe. Scientists still argue about where the real-world boundaries lie. Are we just not clever enough to find the shortcuts? Or are the problems truly, stubbornly hard? Quantum computing may change the game, but even that has its limits. So tonight, imagine your thoughts as problems on a shelf. Some are simple, some are complex, some aren't worth solving tonight. And that's okay. You're not a computer, you're not a solution machine. You're human. And sleep? That's your most efficient algorithm. Now let's descend into a space made entirely of logic gates and binary pulses, where zeros and ones build empires of thought. You're staring at a flickering light. Off, on, off, on. Now imagine millions of these blinking in perfect sequences. Welcome to the world of Boolean algebra, the math that powers circuits, decisions, and the digital age. Boolean algebra deals with binary values, true or false, 1 or 0. That's it. But with just those two symbols and a few logical operations, and or not, you can build anything from a light switch to a supercomputer. It's the Lego set behind every algorithm. Each operation is a rule, and means both conditions must be true, or means either will do. Not flips the state. These rules sound simple, but stack them, nest them, and suddenly you're controlling everything from search engine logic to rocket systems. Here's your quirky tidbit. George Boole, the 19th century British mathematician behind this idea, was initially writing abstract logic to understand reasoning. He had no idea his work would one day run every computer, phone, and digital assistant. He was trying to understand truth, not YouTube algorithms. Boolean expressions are used in programming languages, circuit design, decision trees, even your social media feed. When you set preferences like, show me posts from friends but not about politics, that's Boolean logic in action. Quietly judging every cat video. Scientists still argue how best to optimize Boolean systems for increasingly complex tasks. In circuit design, Reducing the number of gates while preserving function is a delicate, beautiful challenge. It's like trimming a bonsai tree with math. So tonight, imagine your thoughts as tiny switches, clicking softly in sequence. Some turn off, others flicker on. You don't need to process everything. Just follow the logic. This, not that. On, not off. Rest, not stress. The world may be complex, but tonight, your mind gets to be binary. Simple, steady, softly powered down. Now let's meander through a landscape where math doesn't deal in numbers or shapes, but in relationships, flows, and the connections between everything. You're holding a set of boxes. Each box has things inside. Some are connected, others not. You start mapping the connections. Which ones feed into others? Which loop back? Suddenly, your boxes aren't just boxes, they're part of a category. Welcome to category theory, the language of structure itself. Category theory is sometimes called the mathematics of mathematics. It studies systems not by what they contain, but by how they relate. At its core, a category is made of objects and morphisms, things and arrows between them. That's it. But with those two ingredients, you can describe anything from algebra to logic to computer science. Rather than solving equations, category theory looks at how different systems talk to each other. It abstracts and connects. It finds patterns between patterns. It's like zooming out of the math forest and finally seeing the ecosystem. Here's your quirky tidbit. Mathematicians sometimes joke that category theory is like yoga. It stretches your brain into strange, abstract positions. But those who practice it say it brings clarity, elegance, even peace. It's the Zen of pure structure. One of its most powerful ideas. Functors, which map one category to another while preserving structure, like a translator that not only converts your sentence but keeps your grammar intact. Then there are natural transformations, which relate functors themselves. Now you're doing math about math about math. Scientists still argue whether category theory is a tool, a framework, or something more fundamental. Some see it as the future foundation of all math. Others find it too abstract, but no one doubts its elegance. So tonight, imagine your thoughts as objects in a quiet category, each idea connected to another by a soft arrow of insight. You don't have to solve them, just trace their flow. Let the structure carry you, because even in abstraction, there's grace. And tonight, the categories in your mind are gently commuting toward calm. Now let's walk softly into the oldest territory of all, where numbers begin, and counting becomes a philosophy. You're holding one pebble, then two, then three, and just like that, you've entered the world of number theory, where the simplest numbers become the most mysterious. Number theory is the study of integers, whole numbers, and their properties. It sounds basic, but here lie some of math's deepest puzzles. What makes a number prime? Why do primes matter? Can every number be expressed as the sum of other numbers in specific ways? These questions are ancient and still unanswered in many forms. At the center of it all are prime numbers, the building blocks of arithmetic, numbers that can't be divided by anything but one and themselves. They seem to appear randomly, but hide behind them are patterns so subtle, so complex, entire lifetimes have been spent chasing them. Here's your quirky tidbit. The ancient Greeks were obsessed with primes. Euclid proved there are infinitely many over 2,000 years ago, and yet we still don't fully understand their distribution. The gaps between primes? Unpredictable. The largest known prime today has over 24 million digits, far too big to write down, but easily defined with a formula. Number theory is also the secret engine behind cryptography. RSA encryption, for example, depends on the fact that multiplying two large primes is easy, but factoring the result is hard. Your bank login, your Wi-Fi password, your digital privacy, protected by the quirks of number theory. Scientists still argue over things like the Riemann hypothesis, one of the greatest unsolved problems in math. It hints that prime numbers are not so random after all. But as of now, it remains an elegant, whispering mystery. So tonight, picture your thoughts as numbers, some simple, some prime, some beautifully divisible. They sit quietly on a number line, glowing faintly, spaced just far enough apart to be interesting. You don't need to count them. Just rest in their rhythm, whole, integer, perfectly enough. Now let's enter the delicate world where math meets motion, not of things, but of curves, surfaces, and smooth transformations. You're gently tracing the edge of a hill with your fingertips. It rises slowly, then curves, then dips again. But you're not just feeling the shape, you're measuring how it bends. Welcome to differential geometry, the graceful blend of calculus and shape. Differential geometry studies curves and surfaces using tools from calculus. It lets you measure how something changes, how a curve twists, how a surface warps, how space itself might bend. It's the reason GPS works, the reason Einstein's general relativity explains gravity. At the heart of this world are things like curvature and geodesics. Curvature tells you how much a surface bends at a point. Geodesics are the straightest possible paths on curved surfaces, like airplane routes arcing over a globe, following the curve of the Earth. Here's your quirky tidbit. Mathematician Carl Friedrich Gauss once proved that the curvature of a surface can be determined from measurements made entirely within the surface, without ever looking from the outside. It's like knowing you're standing on a saddle-shaped landscape without ever seeing a bird's-eye view. Differential geometry is used in physics, robotics, and even animation. It defines how light bends through lenses, how particles move in space, and how to animate smooth motion across digital landscapes. It's how you create believable motion in movies and accurate planetary paths in science. Scientists still argue about the best way to visualize higher dimensional curved spaces. We live in 3 dimensions, but general relativity takes place in 4 or more. Differential geometry provides the math, but our minds still struggle to picture it fully. So tonight, imagine yourself sliding along a soft surface, up, down, curving left, dipping right. Your thoughts move like beads along a ribbon, following the smoothest path possible. You don't have to steer sharply. Let the geometry guide you, gently, steadily, into deeper rest. Now let's slip into the strange folding world of topology, where shapes stretch like taffy, and what matters is not size, but essence. You're holding a rubber donut. You squish it, stretch it, twist it, but never tear it or glue it. No matter what you do, it's still a donut. In the eyes of topology, it's the same as a coffee mug. One hole, one handle. Welcome to the most forgiving math in the universe. Topology is the study of spaces under continuous deformation. It ignores measurements and angles, focusing instead on properties that don't change when shapes bend. In topology, a sphere isn't about roundness. It's about having no holes. A pretzel, that's a 3-hole torus, thank you very much. The key idea is homeomorphism. when two shapes can be transformed into each other without cutting or gluing. A square and a circle, topologically the same. A shoe and a slice of toast, not quite. It's like math meets sculpture, with only the softest clay. Here's your quirky tidbit. In the 19th century, August Mobius discovered a curious object, a strip with only one side and one edge. The Mobius strip is now a math icon, used in art, science, and even conveyor belts that wear evenly on both sides. A twisty surprise that defies intuition. Topology also studies connectedness, compactness, and other wonderfully vague-sounding properties. It helps explain how surfaces behave, how spaces loop, and how dimensions interconnect. It's used in cosmology, quantum field theory, data science, and even the study of brain networks. Scientists still argue about how to classify spaces in higher dimensions. Some are exotic shapes that defy categorization. And in 4 dimensions, topology becomes wildly unstable, like a dream world where shapes flicker and blur. So tonight, imagine your mind as a shape, not rigid, but soft, stretchable, bendable, every worry smoothed out like dough. You're not breaking, you're transforming. And at your core, your shape remains unchanged. Topology says you can twist, turn, reshape, but you're still you. Always one continuous piece. Now let's sink into the fluid world of calculus, where change is the main character, and motion is told through whispers of slope and area. You're watching a leaf float downstream. Its speed changes with the current. The water flows faster near rocks, slower in the shallows. Calculus gives you the tools to describe all of this smoothly, endlessly. It's math that breathes. Differential calculus tells you how things change. It answers the question, what's happening right now? With a derivative, you can measure the slope of a curve at a single point, how fast something is moving, rising, falling, curving. It's like zooming in with infinite clarity. Integral calculus, on the other hand, steps back and asks, what's the total effect? It adds up tiny slices, areas under curves, accumulated change, the total journey rather than just the speed. It's math assembling reality piece by piece. Here's your quirky tidbit. Both halves of calculus, differentiation and integration, were developed in the late 1600s by Isaac Newton and Gottfried Wilhelm Leibniz, independently, at almost the same time. The result? A legendary feud over who deserved credit. Spoiler, we now give it to both. Sort of. Calculus powers physics, economics, biology, you name it. It models how populations grow, how particles move, how blood flows. Even animation and special effects rely on calculus to simulate realistic motion. Every smooth arc, every falling object, a quiet calculus equation at work. Scientists still argue about the best way to teach it. Should we start with motion, with limits, with intuition or rigor? The math stays the same, but how we feel it can change everything. So tonight, imagine your breath as a curve. Inhale, it rises. Exhale, it falls. Your body, a living function. Your thoughts, their derivatives. Always shifting, always continuous, always smooth. Let change wash over you. You don't have to stop it. Just notice it. Let calculus guide you gently into stillness. Now let's wander into the shadowy corners of uncertainty, where outcomes are blurry and math learns to live with maybe. You're rolling a die. Will it land on 6? Maybe. Maybe not. But the beauty of probability theory isn't in predicting exact outcomes. It's in understanding the patterns of uncertainty itself. It doesn't eliminate risk, it makes it legible. Probability starts with outcomes, the sample space. A roll of a die has 6 possible results. A coin flip has 2. But soon you move beyond games to life. What are the chances of rain tomorrow? Of a bus arriving late? Of you picking the right password on the first try? Spoiler, very low. Then come random variables, functions that assign numbers to outcomes. Your height, your test score, the number of minutes until your pizza arrives. From these, you build distributions, ways of organizing what's likely, what's rare, what's practically impossible. Here's your quirky tidbit. The normal distribution, that famous bell curve, pops up everywhere, from test scores to measurement errors to heights of penguins. Carl Friedrich Gauss didn't invent it, but it's still sometimes called the Gaussian curve in his honor. It's like nature's favorite shape for randomness. Probability isn't just for dice and quizzes. It's in machine learning, quantum mechanics, insurance, medicine. It lets doctors decide treatment plans, lets economists model behavior, and lets engineers prepare for failure. Even if it never happens, scientists still argue about the philosophy behind probability. Is it objective, just math, or subjective, a measure of belief? Bayesians and frequentists debate this late into the academic night. Probability straddles logic and psychology, and it never quite lands on a single answer. So tonight, let your thoughts scatter like dice across a table, each one uncertain, each one valid. You don't need to know what's next. Just understand the shape of possibility. Rest in the bell curve. Let the odds drift where they will. You are not a fixed outcome. You're a spectrum of beautiful maybes. Now, let's drift into the realm of patterns and positions, where puzzles unfold across grids and strategy becomes mathematics in disguise. You're sitting in front of a chessboard. Every move opens possibilities, but behind the strategy is structure, combinatorial choices, optimal paths, and mathematical clarity. Welcome to game theory, where math models decision-making and competition. Game theory studies interactions between rational agents, be they players, companies, animals, or algorithms. Each player makes choices to maximize their outcomes, and each move is a ripple that changes the future. It's not just about winning, it's about outthinking the system. There are cooperative games, where players team up, and non-cooperative ones, where everyone's in it for themselves. Some games are zero-sum. Your win is my loss. Others have shared payoffs and subtle alliances. A key concept, the Nash equilibrium, named after mathematician John Nash. Yes, the one from A Beautiful Mind. It's a state where no player can improve their outcome by changing only their own strategy. Everyone's doing the best they can, given what everyone else is doing. It's math's version of a tense truce. Here's your quirky tidbit. In nature, animals often follow game-theoretic strategies, like bluffing, cooperating, or defecting, without even knowing it. Birds that share food, or fish that clean parasites off others. They're playing evolutionary games, encoded in instinct. Game theory shows up in politics, business, military planning, and even dating apps. Whenever decisions affect others' outcomes, game theory is quietly working backstage, like a referee with a clipboard. Scientists still argue about whether humans are truly rational agents. Emotions, habits, and errors often override logic. But game theory doesn't demand perfection. It just builds a model, one that still, often eerily, predicts what we do. So tonight, picture your thoughts as players in a quiet game. Some cooperate, some retreat, some wait patiently for their turn. You don't need to win. You just need to play gently, with awareness. And sometimes, the best move is rest. Now let's step into a realm where data flows like ink across a canvas, structured not by chance, but by networks, nodes, and whispered connections. You're following a trail of dots. Some connect, some don't. Some link in perfect webs, while others branch like lightning. This is graph theory, the mathematics of connections. Not graphs with axes and curves, but graphs made of vertices and edges. Just points and the lines between them. Graph theory isn't about numbers. It's about relationships. It asks, what's the shortest route? Can we visit every city without retracing our steps? Are these two people connected by a mutual friend or six? It all started with a puzzle. The 7 bridges of Königsberg. In the 18th century, people wondered if they could cross every bridge in the city without repeating one. Leonhard Euler solved it, and in doing so, quietly founded graph theory. Here's your quirky tidbit. That old bridge puzzle gave us the concept of Eulerian paths, trails through a graph that visit every edge exactly once. Today, that concept helps design efficient delivery routes, circuit layouts, and even DNA sequencing paths in biology. Graphs are everywhere now. The internet, a vast graph of computers linked by data, social media, a graph of users and interactions, even neural networks, those learning machines that mimic brains, are graphs at their core. Scientists still argue about how best to visualize massive graphs. When data gets too big, the connections blur. Clusters emerge. Outliers spike. It becomes less about individual points and more about shape, flow, and influence. So tonight, imagine your thoughts as nodes in a soft, glowing web. Some connect tightly. Others drift, lightly tethered. No thought is alone. Everyone touches another, even if the path is winding. You don't have to reach every point. Just rest in the network. Let your mind follow the links, slowly, gently, glowing. You are not a single thought. You're a constellation of connections. Now let's wander into a garden of rules and replacements, where symbols grow like vines and simple instructions bloom into infinite complexity. You're holding a tiny rule book. It says, if you see this pattern, change it to that. That's it. But when you apply it again and again and again, you get something unexpected. This is the world of formal languages and automata theory, where machines read, process, and even understand sequences of symbols. Formal languages are sets of strings built from an alphabet. Think of them as carefully curated patterns of characters. Not just words, but instructions, codes, sequences. If grammar rules your sentences, formal grammar rules these languages. It's how computers know what to accept and what to reject. Then come the automata, abstract machines that read these strings. Finite automata, push-down automata, Turing machines. Each one reads symbols, follows rules, and decides, is this a valid sentence or gibberish? Here's your quirky tidbit. The humble finite automaton, a machine with just a few states and transitions, can recognize patterns like every A is followed by a B. It seems simple, but it's the backbone of text searching, spell checkers, and digital circuitry. This field doesn't just power compilers and programming languages. It helps us model biological sequences, secure communications, and even cognitive science, where our brains are modeled like layered automata, processing sensory input step by step. Scientists still argue about the boundaries between machine and mind. Can automata simulate consciousness? Where does syntax become semantics? Can rules ever mean something, or do they just manipulate symbols forever? So tonight, imagine your thoughts as strings of gentle characters, each one valid, each one accepted. Your mind an automaton quietly transitioning between restful states, reading dreams like language. You don't have to rewrite your code. Just let the rules run. Let the inputs fade. Let the machine hum softly into sleep. You are more than symbols, but tonight they cradle you. Now let's descend into a place where math becomes philosophy, and truth itself is questioned, where even proofs have limits. You're following a clean, logical path. Every step makes sense. Each line flows from the one before, but suddenly you stop. A question arises, not from the outside, but from within the system. Can this system prove everything that is true about itself? Welcome to Gödel's incompleteness theorems, where math meets the edge of knowability. In the 1930s, Kurt Gödel shocked the mathematical world by proving something unsettling. In any sufficiently powerful logical system, like arithmetic, there will always be true statements that can't be proven within that system. Math has holes, not because it's wrong, but because it's too deep to fully map from inside. The first incompleteness theorem says, some truths are unprovable. The second says, the system can't even prove its own consistency unless it's inconsistent. Wrap your brain in a blanket. It gets colder from here. Here's your quirky tidbit. Gödel encoded logical statements into numbers using a technique now called Gödel numbering. He turned logic into arithmetic, and arithmetic into logic, like a mirror reflecting itself. It's the original math meets metaphysics moment. Gödel's theorems ended the dream of a complete, consistent, all-encompassing mathematical system. Hilbert, the great formalist, had hoped for math to be a perfectly sealed structure. Gödel showed that some truths will always live just beyond the edge. Scientists, logicians, and philosophers still argue about what this means. Does it undermine certainty, or simply show that creativity and intuition will always have a place beside cold logic? So tonight, imagine your thoughts as a vast, intricate proof. Most of it you understand. Some steps are mysterious. A few truths lie just beyond your reach, not because you failed, but because that's how deep systems work. Let those gaps be gentle. Let the unprovable sit beside the known. You don't need every answer to rest. Incompleteness isn't weakness. It's what leaves room for dreams. Now let's drift through the world of uncertainty's cousin, fuzzy logic, where truth isn't just yes or no, but something beautifully in between. You're asked a question. Is it hot outside? You pause. Kind of? Sort of? Not really, but not cold either. In classical logic, that kind of answer doesn't compute. But in fuzzy logic, it makes perfect sense. Here, truth isn't binary. It's a spectrum. Fuzzy logic deals with reasoning that allows for degrees of truth. Instead of just true or false, a statement might be mostly true, somewhat false, or 70% likely. It's math that embraces ambiguity, because life does too. It works through membership functions, which assign values between 0 and 1. For example, the concept of tall isn't fixed. Someone can belong to the tall group by 0.8 and to not tall by 0.2. No hard cutoffs, just gentle gradients. Here's your quirky tidbit. Fuzzy logic found early fame in washing machines. Yes, appliances. Japanese engineers used it to design washers that adjust water levels and spin cycles based on how dirty your clothes are, which is not exactly a crisp yes or no question. But fuzzy logic has gone far beyond laundry. It's used in control systems, AI, medical diagnosis, image processing, and even stock market prediction. It models situations where data is imprecise, people are inconsistent, and definitions blur. Scientists still argue how fuzzy logic compares to probability. Both handle uncertainty, but in different ways. Probability deals with randomness. Fuzzy logic deals with vagueness. And in our increasingly complex world, both have earned their place. So tonight, imagine your thoughts as gentle truth values. Not on, not off, just soft. Mostly calm, somewhat sleepy, partially dreaming. Let go of binary thinking. Let the fuzziness settle in. You are not a machine. You're a spectrum. And sleep isn't a switch. It's a slow, soft fade into rest. Now let's visit a place where chaos wears a fractal crown, where the tiniest change can ripple into something vast, beautiful, and unpredictable. You drop a feather, then a second, just slightly shifted. They fall differently. That's chaos theory. It's not about disorder. It's about sensitive dependence on initial conditions. Small changes, big consequences. The classic butterfly effect, a flutter in Brazil, a tornado in Texas. Chaos theory studies systems that are deterministic, fully ruled by equations, but still unpredictable. Why? Because they're nonlinear. Their equations feed back on themselves. Think weather, traffic flow, population growth. You know the rules, but you still can't forecast far ahead. At the heart of chaos lies the strange attractor, a pattern that systems orbit endlessly, never quite repeating, never quite leaving. Like a dream that loops but never lands. The Lorentz attractor looks like butterfly wings. Others look like spirals, webs, or galaxies. Here's your quirky tidbit. Edward Lorenz, a meteorologist, discovered chaos by accident. He reran a weather simulation using slightly rounded input numbers and got wildly different results. His mistake became one of the most influential discoveries in modern science. Chaos isn't randomness. It's structure wrapped in unpredictability. Think of a dripping faucet, regular, irregular, then suddenly rhythmic again. That's chaos, peaking in and out like a shy performer. Even your heartbeat has chaotic rhythm baked into its healthy variability. Scientists still argue about where chaos ends and true randomness begins. Can we ever predict a chaotic system long term? Or are we forever limited to short-term glimpses, like flashes through storm clouds? So tonight, imagine your thoughts as ripples in a pond. One small drop shifts the pattern, sending curves outward. Some overlap, some fade, but all of them are part of the same beautiful turbulence. You don't have to control the storm. Just float within it. Let the chaos carry you softly, unpredictably, toward rest. Now, let's wade into the shimmering edge of reality itself, where uncertainty isn't just a nuisance, but a built-in feature of the universe. You're peering at a particle, tiny, elusive. The more precisely you try to measure its position, the blurrier its momentum becomes. Welcome to the eerie world of quantum mathematics, where numbers describe not what is, but what might be. At the heart of quantum mechanics is a mathematical structure that feels different from anything we've seen. Instead of trajectories and points, we get wave functions, soft, ghostly fields of probability. They tell us the likelihood of finding a particle here or there, but not both. One of the core ideas, superposition, the concept that particles can exist in multiple states at once until observed, and entanglement, where two particles, no matter how far apart, share a kind of spooky link. Changing one affects the other instantly. Here's your quirky tidbit. Schrödinger's cat, the thought experiment, wasn't meant to celebrate quantum weirdness. It was meant to mock it. Erwin Schrödinger was showing how bizarre quantum theory becomes when scaled up to a cat that's both alive and dead. Yet, quantum math doesn't flinch. It works, always. Mathematically, quantum mechanics relies on Hilbert spaces, abstract vector spaces where wave functions live. Observables like energy, momentum, and spin are represented as operators. Measuring something, that's collapsing a vector. Everything feels linear, yet nothing feels predictable. Scientists still argue about what the math means. Is the wave function real? Is measurement a physical process or a mental one? Interpretations range from the Copenhagen stance to the many worlds hypothesis, where every quantum possibility actually happens in a branching multiverse. So tonight, imagine your thoughts like wave functions, delicate, indefinite, quietly oscillating. You don't need to collapse them. Let them spread, shift, blend. You are not one thing. You are possibilities. And right now, the highest probability is peace. Now let's come full circle to the quiet shores where all the patterns, rules, and riddles dissolve into something gentler, understanding. You've wandered through centuries of thought, drifted through numberless rooms of possibility. You've glimpsed the abstract and the infinite, from sleepy algebraic whispers to dazzling quantum waves. But here, at the edge, there's no rush to solve, no pressure to grasp, only reflection. Mathematics isn't just a subject. It's a language for noticing. It doesn't make things more complicated. It helps you see how deeply connected everything already is. And now that you've seen the structures underneath the surface, you understand why the world behaves the way it does, and how much of it still remains mysterious. You've visited realms where numbers can't even be counted, where logic loops back on itself, where uncertainty blooms into symmetry, and where beauty isn't always obvious, but always waiting beneath the surface. Here's your quirky tidbit. Many mathematicians report that their most profound insights come not while scribbling furiously at a blackboard, but while walking, dreaming, or standing quietly in the shower. Math doesn't just live in proofs. It lives in pauses. Scientists still argue over whether math is invented or discovered. Is it a toolkit we made up, or a structure woven into the fabric of the universe? The debate continues. But tonight, you don't need an answer. So tonight, imagine your thoughts as glowing symbols fading gently into fog. Let the rules go. Let the puzzles rest. You've wandered far, and the forest of logic has brought you back to silence. There's nothing left to prove, nothing left to understand, only stillness. Let your breath slow. Let each idea settle like dust in a quiet room. The numbers have stopped spinning, the equations are sleeping, and all the systems are powered down. The world of math is still out there, vast and intricate. But for now, you've wandered far enough. You've seen beauty in logic, comfort in chaos, and even peace in complexity. Let it fade. Let it blur. Let yourself be weightless, unmeasured, undefined. You are not a problem to be solved. You are a quiet constant in the universe's unfolding equation. And now you may rest.